All right, so here we are. We're getting ready to start this new problem. So let's read it and get into it. By listing the first six primes, 2, 3, 5, 7, 11, and 13, we can see that the sixth prime is 13. What is the 10,001st prime number? So in a way, we've kind of already solved this. Like we did the, where is it, up here? We did the prime sieve stuff, I think in problem 2? No, problem 3. Yes. So we did the prime sieve stuff. So one way we could solve this, right, finding the 10,001st prime, is to just keep running it until we find 10,001 primes. There's only one sort of issue, and that's that the way the prime sieve works, you don't tell it how many primes to give you, you tell it how many numbers to check. So like here I've set up a table of 40, and I'm checking that many slots. If I want to keep going past that, I have a problem because I only set up a table for 40 slots, right? So what do we do about that? Well, one thing we could do is just keep growing it until 10,001. So I could try it, 10,001 comes back, then we grab that one. If we try it and less than 10,001 comes back, then we just double our n and try again. So that's like the very easy way to do it. But I think we could do something slightly more fun and interesting, which is we can make a sieve extender, right? We can make a thing that's like, we've already built, we got a list of primes, and now we want to extend that list. So this is going to be mostly an algorithm work thing and not a math work thing. So I'm going to start from the assumption that we all kind of remember how the sieve worked generally, and I'll start talking about how we're going to extend it. I'll review a little bit of how the sieve works, but I'm not going to do it in detail. Problem number 7. Okay. So what we have is like, right now we have the sieve. I'm going to like make a little bit of, I'm going to make some notes on what code we have. We have the sieve, which takes an n to a list of primes, right? And in particular, we can also say that this list is sorted and that all of the n are less than or equal to n, right? So all of the n in the list right? So like that's how our sieve works, is it takes this thing to this thing. And what we want to be able to do is have like a thing that would work like this. Extend sieve is like the conceptual thing we want. And what it would do is it would take a list of primes that we already have. It would take a n low and an n high. Now what n low is it's basically saying here's the previous n we used. So we used this n and we got this list. So then both of those come in as parameters right here. N low and the list of primes. And high is like where we want to go to next. And so that comes out with a new list of primes. And what we want is for this to be sorted. And we want list I'm going to say list I to be n low is less than that and less than or equal to n high, right? Okay, so that's how extending the sieve would work conceptually, but let's think a little bit more literally. When I look at the way I've implemented this, I think I have it returning an array, right? We can go verify this real quick. Prime sieve, primes list. Yeah, so this returns that. Okay, so let's start by doing one thing we skipped before, which is let's tidy up. So when we get back, when we allocate the primes list, we allocate this many slots for it. And what I want to do now is say, after we've allocated that many slots for it, we run it, and then when we're done, we find out the real count. So let's do like a little optimization here where we put back memory we didn't use in the primes list. And so I think we have, let me go check how our code base does that. Is it under memory? Pop amount. So pop amount, you give it an arena, and then the size of our array is, so one element of the primes list times however many we didn't use. So how many we allocated was max value, and the amount we did use was count. So the amount we didn't use is the difference between those, right? So that should give us an optimization where now our arena only has to allocate enough memory for one array. Okay. So here's what's going to be kind of weird about this. If I extend it, then I'll have two arrays. Now what if I wanted to extend it again? I want to be able to make extend something that once I run it once, I then have a new list, and then I could take n high in the new list and feed it back in. Like I want this thing to be able to connect to itself. So this guy here gets the process started, and then after that we can extend it over and over again by taking what we've got and putting it back into this thing. But for that to be possible, I can't use an array here and an array here and an array here unless I have like an array concat, right? You could take like this array and concatenate them. But that would be, you know, some rearrangement work that would have to happen with every extend. So each extend would be like, first you do the extend and then you'd have to do like concat again. So let me switch to my pen here. Then the algorithm would be like sieve, check, extend, check, concat, and then go to extend. Now that might be fine. Like sometimes the right thing to do is to spend a little bit of extra work to make the whole API work in a way where like these things now have this nice property that they feed into each other. But I think we might be able to fairly easily make it so we don't need to do this by tweaking the API. If instead of an array, this thing took in a list of arrays, then when this thing comes back out, it'll give us one array that we can then very easily concat lists. Like lists can be linked lists that are sort of lose high level, large chunks of memory. So like my idea here is like instead of can we optimize away the array concats. That's what I want to find out. I think it's probably doable. So the question is going to be, how will it look when we do it? And I think the idea of this is going to be something like this. So first we get an array, and I'll draw my array like this. So here's an array of primes. And then what I'm going to do is I'm going to stick that into a node. So there'll be like a little node here, and the node knows where this thing is. And then the node has like a null next pointer. But then what I can do is say extend it. So I give the extend the like head of my list, and it outputs a new one of these things, right? And so I get one of these. And then I can go, oh great, let me make a new node, and let me have that new node look at this, and then it'll be the end of the list. And then if I still don't have my answer, I just extend the same list again, and I get another block. So each of these can then be fairly large blocks of primes. And then these over here are the linked list that let us sort of concat this for free. So we'll use fairly large chunks. That way we don't end up paying a large price for all of the linked list iteration. In fact, I'm going to say large block of primes, and over here we have a short linked list. So we're going to build it this way and try to tune it so that these are very large and big chunks we can do in like we can handle each chunk as a batch, and then this list will grow, but it'll hopefully stay short at relatively. I think that would be a cool thing to do, like to work on as some assembly code. We haven't done any sort of like more data structure-y things yet, so I think that's what I want to try. So the first thing I have to decide is if I want to adjust the prime sieve API itself, because if I were doing this in plain C, what I would probably do. Let me find like a good. By the way, that's still not right. I think I checked this out on our first day. Keywords. It still says use comment keywords. So I want to go to user directory, config, use comment keywords. True. It should be working. Yeah, I have no idea why it doesn't work. It's so weird. Anyway. So if I were doing this in just plain C, the way I think I would think about it is I'd look at the API like this. I'd go, okay, so I have a prime sieve API that looks like this. And then I'd be like, well, I'm gonna end up having a prime sieve extend API, which is gonna take in an arena again. And it's gonna take in like an maybe I'll call this like a sieve. Trying to think of like, I don't have a good namespace for this yet, but they're taking like a sieve data structure, and then that sieve data structure would be the list we would have, or this could be like a primes list, right? It's kind of weird. Maybe not, but like low, high, something like that. Range min, range max. It'd be something along these lines. So then the idea is the primes list here, whatever this is, the maybe I'll just call this list U32. That would be a data structure like this. List node U32 has a next pointer like this, and an array U32 like this, and then the list U32 is just a linked list of these, so it's like first, last, maybe we throw in a node count and a total count, something like that. And then what I would ask is, do I really want to return a single array? Because what I really will want is for this to just go in here. So what I might start doing is instead going, hey, instead of returning the array like this, I'm going to have a primes list just be like an in-out parameter that goes through like this. And then you realize prime sieve doesn't even have to be two functions, because this is just the case where it's like range min starts at 0, right? Okay, so I think that's some good API work. So what we're gonna do is We're going to have to write some new assembly to make this work. But I think what I'm going to start with is I'm going to say let's scratch our old wrapper function and write a new one that will meet the API I wanted for this. So primes I before E. And arena list U32 primes min max, right? And the way that will work is we're going to look kind of like the old one. So here we asserted max value. So we're going to have like assert min is greater than or equal to 2. Max is greater than min. Allocate memory. So we get a new amount of memory for primes list. So this is going to be like our new max count instead of max value. Max minus min. We allocate the primes list. We allocate the sieve table. Then we run a sieve. And for now, that'll look like that. We have to adjust this because it's not true that it looks exactly like that anymore. Then fill the result. And finally, put back memory we didn't use in the primes list. And then finally, what we're actually going to do is we're going to say insert new primes onto the list, right? So this will be like the array is this, part of the primes we kept. And then what we're going to do is we're going to allocate a new node. So this will be a list node, push onto the array, a list node 1. On the new node, and then we're going to push onto the list the primes. The new node, we're going to give the primes node count an increment, and we're going to give the primes total count another add from the array.count, and then we're going to put the node's array equal to this array here, right? So we grab a node, we stick it into the list, increment everything for the list, fill in the array part. Maybe do that first, actually. It's a little, I think, more intuitive that way. So initialize the node, stick it onto the array, the list, and then clear out the scratch. So now the only problem is that this right here doesn't actually make sense. We don't have a max value. And I can't just put max count here because then it's just going to generate the list from like 2 to n every time, right? And you know, another thing, this isn't quite right either. So I'm saying min here. I think the first min just has to be 0. Maybe we want to do it like this. So we want one that's like if the, do I have an implies macro? Okay, so if primes node count equals 0, then min equals 0. Let me go add that to our code base. It's under types. implies A implies B is implemented as not A or B. Okay. So assert that implies, okay, so if the node count is 0, then the min is 0. That is required. Okay, so the only thing left is that the prime sieve asm layer is still wrong. So what we're actually going to have to do here is incorporate a new concept. So before we run the sieve itself, we're going to need like a table modifier thing, right? So it's going to be like this. We already have some primes, so let's go back to the way the sieve works now and review that real quick. Not in heavy detail, but quickly. Okay, so when the prime sieve is running, we start with a table that's filled with zeros, and then anytime we encounter something that's a 0 in that table, we know that that must be a prime, because then what we do is we go like, okay, this 2 wasn't filled with 0. It's the first thing we see, so that's a prime. And then we go and we mark all the multiples of 2 by striding by 2 through the rest of the table. And so now they're all marked and they have a 1. So when we get to 4, we know it's not a prime. But when we saw 3, we stopped and put that on the list and then marked all the multiples of 3 as primes, right? And so on until we found all the primes up to the end of our table. So when we are extending our prime list, we're going to have a new table. It's going to like, this would be like if we had another table that starts at 41 and keeps going, then what we would need to do is go, okay, if we're starting at 41, first of all, is 41 prime? In order to find out, we're going to have to check all the primes we've already got and see if any of them would have marked this off. So basically all the primes you've already got get a chance to mark the new table, and then you continue the sieve like normal. So this is going to be like this. We're going to have, and you know, this is where here's the question. Should I write all of that logic? I think I should. So run the sieve will now be a more complicated thing. We'll have the sieve table, which will be all zeros. We'll have the primes list, which is the output. And we're going to need the min and the max. And we're going to need the first node, right? We're going to need this guy, the beginning of the list. So primes first. And then prime sieve asm becomes, okay, so returning a U32. It's getting a min and a max. And it's also getting one of these pointers. All right. So that's how we'll change this, and now we have to write the main logic. So this is the part that allocates memory. It calls the core asm stuff, and then the rest of it is, you know, tightening up the memory, sticking a new node onto the list, and ending the scratch block. So this part here has to iterate a linked list, mix in all of the primes we already know about, and then run the normal sieve stuff after that. So let's get started on that part. Where's our prime sieve? So this, we are going to mark that as the old version and see if we can write a new one. And we'll keep this sort of, yeah, we'll keep that locked in right there. Okay. So the new one, we get RCX through R8D are all going to be, they're all going to be parameters still. R9D is a parameter called max. And there's another parameter. Let's go look up our ABI now. Leftmost. Where is the table that says leftmost? So fourth, and then the fifth one is on the stack. Ooh, we haven't seen that yet, right? So we'll have to figure out. Let's take a look at that part first. Let's just see. This might be like RSP is our pointer, maybe, I think. Like first. Asm proc prime sieve asm end p. All right, so let's start. I'm gonna just like move that into there and see. Extra parenthesis here. What's the matter with this? List. Oh, did I say I would pass you the list? I said I would pass you a list node. Oh, but the list thinks it contains a first last list pointer. Okay. Putback memory we didn't use. Max value is not it. It's max count minus the actual count. Unmatched block nesting. Prime sieve asm old. There we go. All right, I'm gonna need to take a quick break, and then we'll get back. When I get back, I'm gonna step into this and see if we can figure out what this first parameter needs to look like. Alrighty, I'm back. Okay, let's take a look at... Well, I need to call that still. Okay, arena primes give me 0 to 1 million. So up to about a megabyte, no, 4 megabytes even of the first prime. Let's see if we can grab, that could be a lot. Why don't we do like the first 10,000 and then we'll go from there. And the prime C won't actually return anything to us, and we don't really care. So we'll just start like that. And now we want to see, when I run here, okay, grab that, and then we're gonna go into here. And what I wanna see is if I can correlate this pointer here really? Can we? There we go. So primes first is null, right? Of course. What's in RAX is not null, right? Null, not null. So that is not the right thing. Can I do this? No, it doesn't understand. Okay. So let's look at 264 RSP 10. Let's look at 10 of these things on the stack. There's the 0. It's wow, it's 5 in. How am I supposed to find a parameter on the stack? Maybe there's more explained here. Integer value. The fifth and higher arguments are passed on the stack as previously described. All integer arguments are in registers are right justified to the call. We can ignore the upper bits of the register and access only the portion of the register necessary. Any floating point and double precision arguments in the first 4 parameters are passed and depending on the So yes, these are passed by the stack, but how does that work? How am I supposed to find, is that even the right 0? I don't know. Two, three, four, five. Yeah, there are 5 parameters here. So we could do this. We could like look at each of the parameters we're passing. Sieve table, primes list, min, max, primes first. Okay, so there's the 5 parameters. Now, if I go over here, now it loses the values, so we have to grab each of these real quick. Yes, I want that there. Yes, I want that there. This one is easy, that's a 0. Here's a 100, 10,000, okay. And then a 0. So there's the 5 parameters again. So that's my 5 parameters. Now if I come over here, RCX, that's good. RDX, that's good. R8D, R9D, and then what RSP points to is not the right thing. So if I skip 1, I don't get the right thing. What if I like, it's not allowed to like go the other way, right? It's not allowed to be like, I don't think it's allowed to do this. That is a 0. So let's try something a little different here. Let's go over here and view the disassembly for this particular call. So here's the call. And we can see here it's setting up the parameters. We get RCX, RDX, R8, R9. And then here's parameter number 5. So RSP plus 20. And then when this gets called, it becomes plus 28 hex. Right? It's like 1, 2, 3, 4, 5 slots in. How the heck am I supposed to know? Reading from the stack into RAX. It reads that pointer. So this is just like indirection, right? It's reading off the stack the primes. It's reading off the primes the first. And then it's putting the first into the stack at plus 20. Integer arguments are passed in registers. Floating point arguments are passed in these registers. 16-bit arguments are passed by reference. Parameter passing is described in detail in parameter passing. These registers are considered volatile. Register usage is documented in detail in register usage. For prototyped functions, all arguments are converted to the expected callee types before passing. The caller is responsible for allocating space for the callee's parameters. The caller must always allocate sufficient space to store 4 register parameters, even if the callee doesn't take that many parameters. This convention simplifies support for unprototyped C language functions and var args. A prototyped, all arguments are converted to the caller is responsible for allocating space for the callee's parameters. The caller must always allocate sufficient space to store 4 register parameters, even if the callee doesn't take that many parameters. convention. On the stack after the shadow store, before the call. So I think what they're saying, if I'm understanding correctly, if I understand correctly, it's saying that it's going to have to if we're calling another function, we have to allocate 4 bytes, or not 4 bytes, 4 slots. That's 4 times 8. 32 bytes. Even though the first 4 parameters are passed by register, you have to allocate that much space anyways, so that when you get the call, minus 20 is like where your parameters could be found. And then if you need more parameters than what fit inside the 4 slots, it grows anyway, so it's not clear why there's a 4 slot like. Let's take a quick look at this and see if it says anything. Uses registers for the first arguments and the stack frame to pass additional arguments. For details on the x64 calling convention, including register usage, stack parameters, return values, and stack unwinding, see x64 overview. Okay, this doesn't look like it contains anything new, does it? Following 4 examples, each declare an aligned structure or union and the corresponding figure. Aligned to, yeah, we know about alignment. Okay, so my interpretation here is gonna be we're just supposed to know. So like this is going to always be the return address, and then this is an argument, possibly that's an argument, that's an argument, that's an argument, and that one right there is the 5th one, if I'm understanding everything correctly that I've seen so far. I forget, does MASM have a way to do hex? Zero F. Oh, H. H at the end. Got it. Does that work? Am I still running it over here? Yeah, I am. Okay, let's try this. Boom, boom, boom. Now what does RAX contain? It contains 0. So what I want to do now is I want to like play with that for a minute before we call it good. What if I call that with something like I take first and I add 10. So I shouldn't get 0 anymore. I should get something like 160, I think. F10, RAX. 240. 240. So let me check this thing. Oh, yeah. So it's 8, 16, 24 times 10. Yep, that makes sense. Okay, so that is where my parameter is. I find it a little uncomfortable that that's how you find it. But there it is. So now, well, we want to break this down into a couple steps. One, I want to mix in all of the node primes that we already see. So what that needs is a linked list iteration. So that'll look like this. If node equals 0, go to finish mix. Done mixing. So we're going to test. First, what I'm going to do is I'm going to move I'm going to test RAX, and if that is 0, we go to done mixing. Here is our mixing loop. All right. Now the next thing we do is if it's not 0, then we have a pointer to one of these nodes. So to do the increment, we're going to do node equals node next. What we do is we go move into RAX from RAX. So we have the pointer RAX, and we say whatever's at the beginning of that struct, that's our next pointer. So go to there, right? And then we jump back to mixing. So that should give us an iteration across a linked list, speaking of which we can drop this again. Now all we got to do is implement the concept of the loop. So the concept of the loop is a little tricky. I want to think about this part in a little bit more careful terms, because there's weird stuff with the min and the max and whatever. So okay. Thinking through the table index So what I'm thinking about is suppose I have this min and this max coming in, right? So I guess I'll just write that down. I have min and max, and they create a table where min will be max will be more like one pass last. So let me actually go switch to that naming scheme everywhere. It's not just opal, it's first and opal. First and one pass last. So min, one pass last, one pass last, first. Okay, good. So I have a first and I have a one pass last. And then I want to think about so here's the numbers, right? Over here I have the actual numbers in that range, and they form you could think of it like an imaginary table. Now, a few things are going to happen. One, I'm going to eliminate all the even ones. So that could look like this. Or it could look like eliminating the other ones. So this is eliminate evens. And then I want to know I'm going to draw it both ways just to help me think this through. So it could look like that, it could look like this. Eliminate the let me tidy this up. Eliminate evens. So I need to know how to take an index. Well, let me put it this way. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. So I didn't draw the same concept on both, unfortunately. Let me fix it. So there we go. 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So then I have a table that's like this, right? We have boom, 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 boom. And this is our table. And I need to be able to go back and forth from table index and the actual number that we're talking about. So that's what I'm trying to work out how to do. First of all, what I would like to be able to do is say, like, I used to have it, like, here's the way it worked when I didn't have a first and one pass last. I just had I just had the max value that I wanted to reach. Is I would go like, I basically had a special case that was 3 to n, and then what would happen is if I have I stand for my table index and I have n stand for my number, then n was equal to 3 plus 2i. That was the idea, right? So 3 was the first option always, and then you add 1 to the index, you get 1 more than that. Like, you're 2 more than that as the number. So if I then go look at the general case, if I have, let me call it m and n, with the same naming scheme over here, then, oh, and then the other thing I could say is that, like, my stopping point was when 3 plus 2i was less than n was like the valid range. So that would give me, here's conversion, and then this down here is like subtract 3, divide by 2. So I had to remain less than n minus 3 over 2. Okay? Now in the general case, all we're going to do is first we're going to go m prime equals m if m is odd, and m plus 1 if m is even, right? That way m prime will always be the first odd number in our range. Then we just have, I think, the same basic idea. N is going to be m prime plus 2i, and our max is going to be given by m prime plus 2i has to remain less than n, which gives us that I has to be less than n minus m prime over 2. Now let me think about the case over here. So this is true, but what happened when, in here I add the possibility that m and n were even or odd, right? So if n was odd, and I wanted to stay less than that odd number, I'd get an even here, and it would be a integer right here. And if I put an even n in, then say I put in 4, right? Then when you have an I of 0, you get 3, and 0 is less than, okay, so when you put in 4, this actually had to be like that. So I had to be less than or equal to, oh, that's confusing. If n was even, yeah, the way I did this was I treated it as an inclusive range, right? That way if n was odd, it just worked because you'd get like 5 minus 3, and then you'd have a range of 1. Isn't that right? 5, no, because then you'd need a range of 2. Hold on, let me, this part looks like I'm rushing it a little bit. So let me think. How did I determine my bounds? I would have my let me think through a couple cases. So if n was 4, then we wanted to just treat the number 3, right? So our bounds would be here's n, here's the bound. So if n was 4, then the bound on the index was, let's see, it was allowed to be 0, because then you'd get 3, but it wasn't allowed to be 1, so it would have a bound of 1. If it was 5, then it would have a bound of 2, and if it was 6, it would have a bound of 2, and if it was 7, right, so this is how you want it to look. So I want something kind of along the lines of I less than n minus 3 over 2. If I plug in 4 here, and I do a round down, right, 4 minus 3 is 1, divided by 2 and round down is 0. So that doesn't work. You plug in a 5 here, then you get 1, that doesn't work. You plug in a 6 here, you get 3, so this is all just too small by 1. So I think what must have happened is I didn't just throw in a plus 1. That's too sloppy. Let me understand this more cleanly. I want to consider all of the numbers where n is less than n. That's the same as all the numbers where 3 plus 2i is less than n, right? So here, oh wait, no, okay, so that's part of what I'm confusing. When 5 goes there, that's going to be a 1, that's going to be a 2. So that would give me, I mean, I already know what it gives me if I solve this algebraically, right? So if you put in a 4, you get the wrong thing. You put in a 5, you get the right thing. If you put in a 6, you get the wrong thing. So it's off by 1 on the even cases. Because this expression here let me think. So if this wasn't going to be an integer, if you put in 4, then you get 4 minus 3 over 2, so that's 1/2. Right, so this becomes 1/2 of 4. And then 0 works, but 1 doesn't, so 1 is the real bound. Because we only are checking integers, so you don't cross 1/2 until you get there. So really what I'm looking for is like a round up, which I don't remember having that. So let me go read how I actually did this. I might have just been sloppy with what I considered the bounds when I wrote it the first time. Let's take a look. So the old prime sieve, how did it check if we were done? It was minus 3 divided by 2. So like if this was a 3, then R8 was 0. If this was a 4, R8 was 0. And then it was an inclusive range. Okay. We only went to next. loop 0, loop 1 next. No. We only went to the beginning of the loop. Here's where it is. R9 is starting at 0. So R9 starts at 0. As long as R9 is less than or equal to R8, we keep looping. R8 is calculated by doing -3 divided by 2. Okay, so what I'm thinking there is that makes sense. It's an inclusive range. Because this is a divide by 2, we only have 2 cases to think about. And the way it worked out, well, the way I did it, it worked out, right? If you put in a 3, then I has to stay less than 1. If you put in a 4, I has to stay less than 1. What I did was I said, if you put in a 3 or a 4, and you round down and you stay less than or equal to that, you get the same thing as if you put in a 3 or a 4 and round up and stay strictly less than it, right? If you put in a 3 or a 4, you get a 0 either. You get a 0 either way. So it's not about how we're rounding. Saying strictly less than. Okay. So the thing that's changed here is I've gone from wanting an inclusive bound to an exclusive one. So if I put in, before if I put in n equals 3, it worked. If I put in n equals 4, it worked. Now I want it to be exclusive. So if I put in n equals 3, I want something different than if I put in n equals 4. Whereas before they used to be the same. So I think that what I need to do to make it work is to make it n-1 here. Like I need to say, let's just break this down into cases. So we're dividing by 2. So we have case n even. When n is even, we get I less than n minus 3 over 2. Well, 4, if you put in a 4 there, 4 minus 3 so if n is even here, we get an odd number on top, which means we get the same thing as n minus 1 minus 3 over 2, right? And in the case where n is even, or odd, we get n minus 3 over 2, rounded down, is exactly equal to n minus 3 over 2. So if I also looked at n minus 2 over 2 here, if n is even, then I get exactly the same thing as n minus 2 over 2. And if n is odd, then n minus 2 is odd. And so rounding down is like 1/2 less than that expression there, right? So what I actually get is n minus 3 over 2. So it seems to me like if I did n minus 2 here, I get the right result now. Because if n is odd, like if I put in a 3, then I want it to do nothing. So n minus 3, or n minus 3 minus 2 would give you a 1, and 1/2 would then be rounded down, and you would not do any iteration. So we can tell from all of this that I has to be strictly less than n minus 3 plus 1 over 2, rounded down, right? And I think that that will generalize now. So we're saying if we want n to remain less than n, and we want it to be greater than or equal to m, well, when I equals 0, n equals m prime, which is greater than or equal to m. So this, the left-hand part is like free, because we never make I less than 0. Yeah, if I is greater than 0, say it like this, if I is greater than or equal to 0, m prime plus 2I n equals m plus 2I is greater than or equal to, well, hold on, let's do this. M is less than or equal to m prime plus 2I is exactly equal to n. So the left part holds. And then for the n less than n part, these are like separate. Okay, so for the n less than n part, we just need the same thing we did over here, n minus m n minus m prime plus 1, right? I think we want to use m prime so that we know that this is odd. That'll tell us how the whole thing rounds. So this is the first possible value, and we're just saying I needs to be less than this, which is easy to do. Right? We can do that. Running, right? Okay. How do you do bitwise OR? Because a bitwise OR would do what we need to do there, right? Bitwise. These are like vector related things. Is there just like OR W, or is there just something called OR? I get bitwise logical OR. Nope. Bitwise logical OR. Or PD or PS. P or 1, 2, 3, 4. I don't know which one of these works on the non-vector stuff. There's got to be one that just works on like your standard register, right? K or W, bitwise, logical, or PD, or PS. These would be also. Yeah, what's going on here? Already looking at this one. Is there not just an instruction called OR? Here it is, OR. Did this one not say logical inclusive OR? Okay, so yeah, it just didn't show up in the searches I was using. Okay, so OR R8D1. Does that work? First, opal. Okay. Greater than or equal to first is strictly less than opal. Yeah. Yep, okay. So we've done that part. We've got M prime. Now we can figure out what our iteration bound is going to be on the, I'll call this I bound. That's going to go in, that's going to be max. These are like opal, first, wait a minute. First, opal, first node, node to racks. Let's see, so here's M prime is an R8D. Then I bound is one pass last minus M prime plus 1 over 2. So I don't think I need one pass last to be preserved. So I'm going to put this into R9 now. So we're going to subtract out of R9, R8. We're going to inc R9 by 1, and then we're going to shift right R9 by 1. So that should give us our I bound. So R9 is our bound, our minimum bound, or our maximum, our index bound. R8 is the M prime we use for conversions. And then test, if that's 0, we're done mixing. So then what we want to do is say, so we now have a node. And what we want to do with the node is we want to figure out, yeah, we're going to put it's going to get interesting. Table memory we need right now. Primes list. Primes list we don't need. So I'm going to sub RSP by 8. That makes this now a 3-0. At the end, we're going to have to add RSP 8, but we can start saving certain things for later. I'm going to move into RSP the primes list. We don't need it for now. Now RDX is free, so we're going to make RDX our pointer. And that means that we move into RDX from RAX. And then let's see, here's 0, then there's an offset of 8, and then there's an offset of 16. Oh wait, no, that's the count. We'll also figure out what the bound on this thing needs to be, so we'll move into, let's see, R10. The count, so that's RAX plus 16. Then we have to mul R10 by the size of one of these things, so that's going to be like shift right by, let's see, we're multiplying by 4, so shift right by shift left by 2. That should multiply by 4, and then well, I suppose what we could do here is load effective address, right? So we have V in RDX. So we're going to put into R10 RDX plus what we already have in R10 times 4, right? There we go. So this is the base of the array. This is the count of the array. And then when we multiply that by 4 and add it to the base of the array, we get the end of pointer of the array. And now that's in R10. Now we can do a loop that's going to be like this. This will be mixing 0. This here will be mixing 1. And this is going to go if RDX is greater than or equal to R10, then go to mixing next. Mixing next will be right here. We have like a loop inside a loop situation here. So test, compare RDX with R10, jump if greater than or equal to mixing next. And otherwise, if we didn't jump now there, then what we're ready to do is read out a prime and mix it in. So we're going to read a prime, so R11, right? I don't think we have anything else that we want to ditch right now. We want to keep the node in. Yeah. So R11 is going to equal star RDX, which is like our pointer. So we're going to move into R11 from R11D, D word putter. Then we can just do it like this, RDX. So move 4 bytes from this pointer into this register. And then we have the prime. So once we know what prime in the list we are going to mix, all we have to do is convert that prime to its first position in this list. Now that's not necessarily trivial. So let's take a look at how that works. Where did my stylus go? It's hiding back here. Come on out, okay. Okay. So given a prime P and a range M prime to N, how do we find the smallest x in the such that P divides a prime P, P divides x, and M prime is less than or equal to x is less than or n if such x exists. So that's what I want to figure out next. So we want to, I think what we could do is we could ignore the n part first and just find the next multiple of P greater than or equal to M prime, and then test if it's in the range before continuing. That's how we could think about it. So how do we do that? If I have so my multiples of P will be spaced out like this, right? So I'll have like I'll have x minus 1 P. That will be less than M prime, which will then be less than or equal to xp, right? Or I guess I should say k. K minus 1 and kp. How would I find a k like that if it existed? Well, what I could do is M prime, if it's equal to kp, then it's just k equals M prime over P. If it's less than kp, we can figure out so I think that the answer is going to be something like this. So if M prime equals kp, then k equals M prime over P, right? So it's just a division. Now, if it's going to be division, then after we get M prime over P, we'll also have M prime modulo P. And that'll tell us how much, that'll tell us the remainder of, okay, right, so otherwise, R, or otherwise M prime modulo P, the remainder, will be equal to M prime minus K minus 1 P, right? And then we can solve for K, because we know all of these So k will then be let's see, k minus, one case, k minus 1 p equals m prime minus m prime modulo p, k minus 1 equals m prime minus m prime modulo p over p. And then k equals m prime minus m prime modulo p, right? So I'll have this remainder, I'll subtract that out of m prime, and then I'll do the divide, and then I'll add 1 when I'm done. That's how it'll work. So really what we're talking about is just rounding up, now that I think about it. Okay, let me back up, because there's a simpler way to say all this, I think. All that was true, but we could do it another way. We're trying to find k, because once we have k, we do k times p, and we get our result. If m prime divided by p is k with no remainder, then m prime is just our answer, right? Because we have k times p is already known. But if k times p does not equal m prime, then what we're going to want is, either way, I think what we end up wanting, I guess I should say, is that x, yeah, here we go. I just erased like all the thinking. I don't know why I do that, but x equals we're going to say up here, let k such that, such that pk k times p equals x. So we know that x equals kp, so if we can figure out how to compute k, we're done. How you compute k is you do m prime over p rounded up, and that's how you get k, right? See what I mean? So if this here is exactly an integer, then this will be equality. If this is less than an integer, then m prime is not quite as large as k times p. And when we do the round up, that's why, right? The rounding up makes kp bigger. But it'll never get to the point where k minus 1 times p is equal to m prime, because as soon as that would happen, then k is 1 less, right? As soon as m prime is divisible by p, so that k minus 1 times p is equal to m prime, right? Then it's divisible by p, and the quotient is k minus 1. But then this whole thing finally, k goes down by 1, and so you then have that it's actually on this side again, if that makes sense. So the computation is just going to be computation we need is going to be, let's see, m prime x comes from m prime plus p minus 1 over p rounded down, since that's what we can actually compute, and then times p. That's not so bad. So there's our p-value. Let's try to compute x. X equals, now we just had this, m prime plus p minus 1 divided by p floored times p, right? So x is going to get stored. We want to keep p, so we're going to store x into R12. So we're going to move into R12 our m prime. Where did we store m prime? Here's m prime, it's in R8. We're going to add into R12 our p, that's in R11. We're going to decrement R12 by 1. We're going to, now we're going to have to, okay, are we using RAX for anything? Yeah, we're trying to use RAX for the node, but that's just not going to work. Table memory is necessary. So yeah, this is going to have to move into something else. So let's put that in R15, I guess. R15, RAX, R15, R15, RAX, R15, R15, R15. Is RDX storing something important? RDX is our, yeah, that's not going to work either. We have to steer clear of that one. So this will be R14, R14, R14. So that's our array. Our pointer walker thing. Here we need to use R15, R15. So that's good. If RDX, so this means if R14 is greater than or equal to R10, we go there. Okay, here we go. The mixing loop. This should probably be called mixing 0 next, because it's the next part of the mixing 0 layer. So mixing 1. If the pointer is big enough, we read the prime, we compute x. We need to compute x by, first of all, we're going to put this all into RAX. We're going to clear out RDX. Hopefully we finished. Yeah, so this primes list gets saved for later. Then we do the divide by p. That gives us the floor of divide by p in particular. And that p still lives in R11. So now RAX contains the floor, and then we IML the R11 back in, and now RAX contains x, right? Okay, before I do the main thing we need to do, I'm going to write the end of the mixing 1 loop. So the mixing 1 loop goes like this. We increment R14. So we add to R14 by the amount that's in the prime. The prime is R11. No, wait, no. We add 4. Right, R14 is our pointer. It's walking along a bunch of U32, so we just add 4, and then we jump back to mixing 1. Okay. Test if we can keep looping. Okay, so each step we get the prime, we get x. Okay, now what we can do is we got to test and see if this thing is in the table, right? if it's in the table, we can mark it. If it's not in the table, we have to skip. Now, just because we're skipping doesn't mean we're going to skip the whole thing. So this is where we have mixing 1 next, right? So we skipped mixing 1 next here because 1 prime might not show up in the table, but then the next prime. So what I'm trying to say is, like, it might be that 1 prime is fairly large, and so it's prime. Well, let me think about this. If a particular prime P doesn't show up in the range of the table, the next one has a larger range. But that doesn't mean it doesn't show up. That's the thing. Something with a fairly large range could still show up if it happens to land there, right? It'd be different if we were saying, like, look, when you take this prime and you multiply it by 2, it's already too big to even be on the max. Then we can quit completely. So we'll throw in an optimization here too. Optimization, quit mixing when 2p is greater than or equal to opal. Okay. So we computed x. Next we're going to do is if x is greater than or equal to opal, go to mixing 1 next. Compare. How can I do this? I said that I wouldn't need to keep R9. But maybe I should have. R13 is going to be coming into play now. I need to start saving all these. So push R15, 14, 13. I think 10 and 11 are in play, and those are also call or save. Right? Call save, are they? I can't remember now. Non-volatile. So 12 is the first non-volatile one. So 10 and 11 I can use, but 15, 14, and 13 I need to manage those. And what's most annoying is each one of those that I add is another 8 here. So 1, 2, 3. How are we looking so far? Okay, I want to compare x, which is in RAX, with OPL, 1 pass last, which is in R9. Jump greater than or equal to mixing 1 next. Okay, if that didn't happen, then it's mixing 2 time. So this is the loop. So we have one loop that's looking over the nodes. We have a second loop, it's going over the elements of the array. And then at each element of the array, it computes x. And then it does this test and possibly skips the work. But if it does the work, then the work is to start at x, mark it in the table, and then increment by p until we are outside of the table. Actually, this could be the mixing 2 loop here. So we don't know, it might be skipped right away, but we go ahead and test it every time. And then if it's not skipped, we go mark x, and that just means we want to move into, where's our table memory? RCX plus, we need the index. So we need to figure out what value j has. We'll put that into a register that's free in a minute here. Something, put in a 1, right? It's like some index times, no, some index, we gotta figure that out. So now we just have to compute. Oh, okay, so we computed x. or comparing that against one past last. Ah, that's what I screwed up. Okay, so we computed x, but I don't actually need, okay, so R13, I'm gonna keep that one reserved, but we don't actually need the bound because it'll be easier to not use the bound and actually, to not use the one past last and to just use the bound. So this becomes R9, which is one past last, minus m prime, which is R8, plus 1 divided by 2. Good. And then this becomes, we compute x, and then we need to compute j. J is just this other thing. All right, so here's x, here's j. J is I didn't write the conversion the other way around, but let me write that down real quick. So the other way to think about it is that I equals n minus m prime over 2. M prime will be odd. We already know n is odd because we are looking at primes, except for the case of 2. So that's another thing I have to do. If all right, let's do this part first. If p modulo 2 equals 0, so if we have, well, let's just do if p, oh, it's an easy one to test. If p equals 2, I don't think you can compare to a constant, can you? You have to compare between two registers. Or can you do an immediate? Hey, you can do an immediate. Okay, if p equals 2, go to mixing 1 next. So we don't think about p equals 2. It's a case we don't actually put into the tables. So compare R11 to 2, jump if equal to mixing 1 next. So we just skip that prime, and then we increment our pointer and go to the next step of the loop, mixing 1. Now, to compute j from x, we want n, or x in this case we know is a prime that's not 2, so it's odd, minus m prime, which we know is odd, so we will get a nice clean division here. X minus m prime divided by 2. There might be some way to compute j without computing x, but like it's kind of confusing, right? Like this gets put in here, added in, and then rounded down. I think you would still end up having to do this division to figure out if it was gonna round down or up or something. I think this is fine the way we're doing it. It's probably not easy to make it, it's probably not trivial to make it like skip the divide if it's possible at all. I really think you would end up needing the remainder even if you didn't rely on the full divide. Maybe you could skip the multiply, but let's do it this way. So j is going to get x minus m prime. So sub from RAX, m prime. M prime is R8, I think. Is that right? Yes. And then divide by 2. So shift right RAX by 1. So there we go. Now RAX contains j. So when j is greater than or equal to I bound, then we skip it. So j is greater than or equal to I bound, skip. Then we mark x. So what is x? Well, x is the beginning of the table of, so here's our memory. It's not the primes list, it's the zeros and ones table memory, plus j. J is our index into the table now, right? So that's in RAX, and then we just mark that with a 1. Okay, so we mark x in the table, and then we do increment j. So add to j. So this is like j plus equals p. We increment by p. Where did we keep p, the prime? It's in R11. So add to the thing containing j is RAX, add in R11, and jump back to mixing 2. So then that should give us just a nice tight loop where all we're doing is we're going compare, jump out if we're done, move a 1 into this position, If you were really clever, what you could do is you could figure out that you don't even really need to be doing an add here. So something I need to learn is whether or not these adds are worth skipping. Like I get the impression that it's like at the microarchitecture level, you pay for an add here. It's not like because it's one instruction, it's free, right? Which means if you made it so that RAX was a pointer and you were just doing this, and then the compare was against some other bound, like RCX plus R13, that really wouldn't be that hard. So let's do it. R13 isn't in use anymore, but we kept saving it, right? Yeah. So what we're going to do is we're going to set R13 is equal to RCX plus iBound, right? So that's like the end of the table memory that we're allowed to write. I'm just going to keep that here. Add into R13, R9. So there we go. There's the tables one past last. And then we just need to say, boom, footer equals table memory plus j. So we add into RAX the table memory. And then here we're doing footer. Here we mark the footer with a 1, and here we increment by p. It doesn't know how big it is because it's an immediate. It's not a D word footer. Oh man, what is it when we want to move into a single byte? Mov into. I know we wrote one of these before, but I won't know. It's going to be in the sieve, the old one. Somewhere in here we have a move of 1 for marking the table. Byte putter. Okay. So let's, we don't have any way to test any of that yet, but that should actually do the whole thing, I think. So let me review what we've done. It's a lot of code. We're saving some registers up front. Hopefully this is finding our node pointer and putting it in R15. We're saving RDX for later, the primes list, because we need to use RDX for divides. So the primes list gets saved for later. We don't need it right away anyways. That's like the output list. We then compute some stuff. So M prime is what we do to modify first. Or, yeah, to make it odd. Here we calculate the iBound, and here we calculate the table memory bound. So the I bound is the largest, or the one past last of the table, like the indexing. And this here is just the same thing, but applied to the table memory. So it's like the table memory plus the I bound. Then we have the mixing loop. And the first thing we do is we say, test our node pointer, and if it's 0, we're done mixing. Otherwise, read the v pointer out of this node and read the end of that array by grabbing the count, which is at the node plus 16. This was at node plus 8. So node plus 16, and then using LEA, we add that together. So we get the beginning of, this isn't quite right. This should be R14. The beginning of the array for R14 plus the end of the array, which is R10, the count, times 4. And we put that all into R10. Okay, so now we have it all set up, and we go into the next step of mixing. So here we read the node. Here we're iterating an array of primes. We check if we're at the end of the array of primes by testing the pointer against this bound we set up. And then if that doesn't jump us out of the loop, we grab a pointer out of we grab a prime off of this thing here, R14. That's our pointer for the array. We put that into there. So we have 4 bytes of a pointer there. Then, if that's a 2, we just skip it. We haven't done this part yet, but we could do it right now. If this is where having the one pass last preserved would make things easier. 2 times p is greater than or equal to opal, go to done mixing. Okay. So here's how I'll do that. First, I have RAX is currently free, because I'll start using RAX down here, but I'm not carrying it over anything from up here into that RAX. So we can use RAX to grab the prime. We can double it, shift left by 1. Now we need someone to remember the actual value. So R 13 or R12 is going to have to get into the mix. R12, this becomes 50, pop R12 down here. Okay. Okay, so we save all those registers. Now R12 is available. We have the one past last getting romped over here. I think we'll still do that, but first we're going to move opal into R12. Okay, so R12 is going to remember our one past last, and R9 is going to get modified in place to be our I bound. And so R12 is the thing we compare to for this thing. So RAX computes 2 times P, and then we compare RAX with our one past last, R12, and jump if that's greater than or equal to done mixing, right? So if we are going along our primes, when we get to a prime, we know our primes are sorted. So if we get to a prime where the next factor, the next multiple of that prime is past the end of the range that we're even interested in marking, then none of the primes after that will be worth looking at either. Okay, next what we do is we say, all right, so we have a prime and we know we need to check if we can mark it. Like it's plausible that we could mark it. So now we go ahead and compute x. X is the first multiple of p in our range, if it's possible to put it in our range. Then we compute the index from that. and then we compute a pointer from that, and we then finally go into the mixing 2 loop. So this loop is really tight. All this has to do is go check if we're done, like check if our pointer's past the end of the memory of the table, mark a byte in the table, and then increment our pointer and go to the next one. And that just goes on and on and on and on and on, right? There is another trick we could do, now that I think about it, which is we could apply the squaring trick still. So after we compute x, we could say, okay, so this is giving us the first x, which is the first multiple of p in our range. But we could also say, look, you shouldn't be using anything less than p squared. So what we're going to do is we're going to first compute k. And if k is less than p, we just set k to p. That's how we'll do this. So how we compute k is everything besides the mole. So RAX contains k, which is m prime plus p minus 1 divided by p. And then if k, so RAX needs to be preserved. Is there anybody we can trash right now? RBX, I think we're gonna have to just grab more Kali save registers, I think. Let me think about what we have used. So R9, 10 and 11 are all in use, I know that. 8 and 9 are in use. RTX, RDX, RAX, RDX is free. Okay, RDX is free. So what we can do is, if k, we don't need to square it. If k is less than p, k equals p. So we're going to compare k. K is the register RAX. P is the register R11. Then conditional move if less than, right? I think that's the way you do it. Conditional move into RAX, the R11. Let me go double check the conditional move stuff. Conditional move stuff. Okay, do we have like conditional move if less? Yep, right there. There it is. Conditional move if less. So what that should do is we do this comparison and then we change RAX to R11 if k was something less than that. So then when we do k times p, we're getting p squared. And when we compute the index, we're getting the index of p squared. And we're doing that because if you don't understand why we can do that, go watch the original pass on the prime sieve. But the first spot in the table you should be marking is always, oh crap. The first spot you should be marking is always p squared. And then we can actually use that to make this logic even better. So let's compute k first. And then let's do this. If here's what I'm gonna do. If j is greater than or equal to I bound, then, wait, no, that's not right. So it is true if p squared is greater than or equal to 1 past last, then we should be done. But I should check that up here. Okay, if I did it based on the index, then the problem is it's possible that something's, well, if it's too big, if the first one is too big now, it's confusing because when you do this divide by p and round up, Yeah, this part here is a little confusing. I think we should just test it way up here though, because it's pretty easy to do that. So what I want to do is RAX becomes p squared, and if that is greater than or equal to our one passed last, that's the first one we would start marking, and it doesn't fit. So we just are done. That'll let us get done very early. And then if we're not done, we compute k. K is the thing you have to multiply by p to get over m prime, at least up to m prime. So here's k. And then if k is less than p, that means that p is large enough. P is like that p squared is going to be markable because we didn't skip it. But it's not going to be it's big enough. So p squared is markable, but the k, like something smaller than p squared, is already on our table that we can skip. So this is doing the skipping to p squared part. This right here. Then we compute x, so that's either p squared or something bigger. And we compute j, which is the index into the table that represents the number x. And then we compute our pointer, which is the actual pointer into the memory, found by adding the pointer to the base of the table to our index. Then we run the loop. If that gets done, it'll jump to here, where we'll look at the next prime and keep mixing. If we get to the end of a node, how do we know when we get to the end of a node? How do we know when we get to the end of a node? So if we are at the end of the array of pointers, then we go to the next step of the node iteration here, and that'll terminate if we're at the end of the node list, even if nothing else worked. So I think all of that's good. All right, so we've now done step one. Our table is no longer just full of zeros. We are sieving, but we have a sieve with primes that have been inherited from a previous list. So a bunch of them are already marked. Now what we do is just the part where we scan along and discover new primes. So that we can copy paste from the old sieve, because that's like part of how all sieves work. So we already wrote that for the original sieve. Let's go look at that. Old not bounded factors, yeah, prime sieve old. Okay. So when we're done mixing, what do we do next? So we need a special case that's like emit to if, yeah. So at the very beginning, we need a special path because 2 gets special cases. So we grab our node pointer here. We're just going to say if node does not equal 0, go to skip emit 2. Test R15, R15. Jump if that is 0 to skip emit 2. Skip emit 2 is right here. And then here's our emit 2, right? So we'll do that. Right, and then what we're going to do is we're going to use RDX as, wait, we use rdx at the end, don't we? Okay, so here we save the original list of primes. Oh man, I think I might need to save two things. Let me check over here. I think I used rdx at the end, or I have, yeah, rax is separate, and then we return it at the end. Okay, got it. So no problem. We're just gonna have to save two things because we kind of need to do this after this. Well, let me do it this way. So here I save the list of primes, the base of it, and rdx here we're going to add 4 because that's our increment past the first. I assume I had like an XOR. Okay, I see. So this is going to be, RSP is going to be our primes list. RSP plus 1 is going to be our counter. And when we emit 2, we're just going to move into the counter a 1. So it's a little special case that we need for emitting the 2 on the first node. Okay, so the 2 comes out. What else do we have? I don't know if we need x not r9 equals 0. Let's see, r10 equals table memory. So here we need to do, okay, so there's mixing done. Then what we have is I'll call it like scanning 0. So scanning 0 is we'll use rax to read the table memory. Well, hold on. First of all, let me decide like what registers I do and don't have the right to use now. Okay. I'm gonna want to read these things out. So retrieve base of primes list. RDX is RSP. Retrieve counter. That'll go into RAX. So those things we saved earlier so that we could use those registers during the mixing phase, now we're pulling them back in. So we've retrieved those things. What else? What else do we have? Scanning 0. Oh, I'm on the wrong function. 0. Okay. Wait, no, I remember what I was doing. So I've retrieved those things. I'm gonna need, let me just read how this worked. It's reading from the memory, testing it, converting, yeah. So this has to look a little different because, well, actually we can totally do this. Yeah. So this won't be a 3, but it'll be m prime. So let me write down the steps here. Scanning goes like this. read the table memory, table byte, test the table byte, compute P from J, emit P, compute J from P squared, and then we have the scanning one loop. Okay, so I've got the basic idea there, and then scanning 0 next. Right, that's how I was marking these before. Yeah, so scanning 0 is the next phase. Looks like we increment through our table. All right, so up here we need increment table pointer, test table pointer, and then we're done. Yeah, okay. So let's set these things up. Who's going to be our table pointer? I think R12 is done being one pass last, so we're going to say make R12 the table pointer. R12 from, where is the table pointer? Actually, RCX. Yeah, that's fine. No, we don't have to do anything. RCX will be our table pointer. So let's go write the things we need to do there. So read the table byte. Who will be the thing that contains the table byte? That could be R12. We don't need a node pointer anymore, so let's start with R15. Work our way down. So move into R15 from RCX. Byte putter, B, right? Byte putter. Yeah. Well, I mean, that's just me. I see. I was doing mov ZX. Okay. So give me in R15 the 0 extended value after you read a byte from there. Then we test that. So what we want to do is, if that's a 1, we just go to the next. So if that's not 0, if mark does not equal 0, go to scanning 0 next, right? Scanning 0 next. So that's if mark does not equal 0. Now, what if we compute that and we go, okay, now we want to increment the table pointer. So this is going to be putter plus equals 1. That's like inc RCX. If RCX is greater than or equal to table, so if putter is greater than or equal to table memory bound, okay, if it's less than table memory bound, go to scanning 0. So compare RCX to our table memory bound, R13. Jump if that is less, back to scanning 0. Keep going. Keep doing more work. So one thing that's different is I'm not keeping a J value. So I'm going to need to compute J from putter whenever I don't skip through this part, right? So where am I going to put j? I still think I need I bound, right? I might not need I bound. I might be able to compute j from putter. So this would be like j prime compute putter prime from j prime, and then do scanning one loop. Yeah, that'll be fine. So we don't need R9 anymore. In fact, we didn't need R9 anywhere after we set it up. Interesting enough, we just use table bound everywhere. Yeah, cool. Okay, it's gonna take so much debugging, I think. So let's compute j from the putter. So our putter is where? That is RCX. So we're gonna put this into R9. R9 is, I don't think we need OPL anymore, so we could also be using 12. What is R14? Who uses R14? R14 is totally free. It's only, yeah, R14 is only used in one, like inside of mixing 0. So until the end of a one mixing 0 case. Once we jump back to mixing 0, R14 becomes free again. And if we jump out past the end of the mixing 0 loop, R14 is free. So R14 gets the value of putter minus, oh, here's an issue. Yeah, if we just use RCX, we still need somebody somewhere who knows the original value of the table. So what I'll say is, let's make R12 R12 our putter instead. R12 gets the value from RCX. Putter minus table memory. So this gets R12 sub RCX. RCX becomes R12. We're inking on the putter, testing on the putter, table memory bound. So R13 stays allocated. We can't use R13, but we're using 14 here. We're using 12 here. Okay, so 14 is J. Now, I don't think we need J anymore, so let's compute P. So P equals M prime plus 2I. So M prime plus 2 times J. So we're going to load effective address R14. So our base is M prime. Who has M prime? R8. And that's plus J, which is R14 times 2. So that should give us P. And then we want to do an emit. So an emit works like this. We D word putter something, the R14 D word. Okay, now we just need to figure out. So here's primes list, RDX plus RAX, the counter, times 4, inc RAX. Okay. So now I want to compute J prime from P squared. So p squared, we already used p, we don't need p anymore, so we can trash p with p squared. So that means we can imul R14 to itself to get p squared in it. Then to compute j prime, we take an odd number, R14 is an odd number, we subtract, so j prime equals p squared minus m prime over 2. So we subtract R8 from R14. That gives us p squared minus m prime. Then we shift right R14 by 1. That gives us j prime, the index. Finally, we get our putter prime. So putter prime equals j prime table memory plus j prime, right? So our putters are putters at the table memory. So putter prime is table memory plus j prime. And now our scanning, oh, wait, let's compute that. So we can trash j prime now. Add into R14. Where's our table memory? I think it's an RCX. Yes. Okay, so now R14 is putter prime, and we begin scanning 1. So here, the test is, we've actually written this test before. We want to make sure we're not going past the memory bound. So compare R14 if putter prime is greater than or equal to table memory bound, go to scanning zero next. So that's how we jump out of the loop. The like second loop, the scanning 1 loop to go back to the scanning 0 loop. We compare R14 putter prime to the memory bound, which is R13. If that's greater than or equal to, we go to scanning 0 next. So this is our marking loop, is another way to think about it, right? So there we go. Now what we want to do is mark X in the table. So move a byte putter at R14 1. So we put a 1 into the table, and then we do so this is basically star of putter prime equals 1, and then putter prime plus equals 1. No, plus equals p, right? Add to R14. Where's our prime? Oh, we trashed the prime. We thought we didn't need it anymore, but we did. Okay, so R14 can't be our... Who is not getting used? Looks like R10 is probably free. What was R10 used for in the other steps? So R10 was the bound on the array, so we can use R10. So R14 is our prime right here. We emit R14 right here. We're going to make R10 our J prime. And then our putter prime, R10, it's a 1 in it. And then we add to the putter prime R14. So R10 is our putter prime, R14 is our P. We add that P into the putter prime. That increments our way along the table by however big the prime is. And then we jump back to scanning 1. got some mistakes. Yes, this doesn't know how big it is. And this also doesn't know how big it is. And that doesn't know what that, I didn't type it correctly, so it doesn't know what to make of it. And now, when it's all done, I think we've written it at all. So when it's all done, what'll happen is it'll be scanning along and it'll go, hey, the table, we've gone to the end of the table memory, and so we don't jump ahead. So then we restore the stack, we restore the registers from before, we restore the stack value to where it was, and we return RAX has been our counter this whole time, so that's what we are supposed to be returning. That should do it. Except for the bugs, right? Obviously, we're gonna have to figure out what the bugs are. But let's take a look. So if I prime sieve several times like this, prime sieve 1,000, 10,000 to 100,000, and then 100,000 to 1,000,000. So I should be able to keep on extending the prime list this way. So let's go debug all this. Run. Ah, right. So the first is supposed to be 3. Alrighty, so that's all normal stuff. Trusting here, like basics will make sense. Let's look at the registers window real quick. So RDX is our primes listed some pointer that gets stored. 0 gets stored there. We grab the node pointer. No, that's not right. All right, so we need to figure out where the node pointer has gone because we've lost track of it again. Give me the last like 80, well, no, let me do more than that. Wait, why is it doing? Give me the last 1,600 bytes. Well, if it's gonna, no, okay, let me see. 100, because it's not bytes, it's U64s. So this right here is the pointer from RDX, right? No, what am I screwing up? Did I already overwrite RDX or? Well, let's just look at it again. Boom, boom, 3, 4, 2 more, 2. We move that into there. Okay, so yeah, that's that. That goes into there. Those are the values of R15 through 12, R12 through 15 that we're trying to restore later. So they'll live in there. We move the node pointer to R15 and we get it wrong. It's actually living at 88. And I think we have it on hex 50, which is 80. Yep, 496. Boom. So how did we get it wrong? 1, 2, 3, 4, 5, 6. So it was at 28. Right, so there's 6 here, plus the instruction pointer is 7. So 1, 2, 3, 4, 5, 6. Instruction pointer is 7. And then there's... Wait, 1, 2, instruction pointer... And then there's 5 more. It's so weird. Let me just see that again. So here it is, 1, 2, 3, 4, 5. So it's initially at 40, which is like 1, 2, 3, 4, 5, 6 slots in. I find it very strange. That's all I can say. How am I supposed to know when I'm getting called the offset into the stack for that parameter? That seems weird to me. It's It's not like any of these are filled with that information, is it? No. So it starts off at 40, which if I like look at that as hexadecimal is something smaller, but then it goes up by 6 more and ends at 88. So I think this just is one too small. I probably forgot to increase it when I did R12 or something. So R15 gets a 0. If that's a 0, skip if... Okay, so that's wrong. Jump 0, this should be jump not 0. So if this is not 0, we skip the emit. But it is 0, we do the emit. So boom, we do the emit. So we put a 2 right there and a 1 right there. That puts a 2 in the first list and a 1 into the counter. Now we're going to compute m prime. M prime is 3. We're going to compute 1 past last. Yes, we put all 1 past last into R12. And then we rearrange R9 to be our I bound. We rearrange R13 to be the memory I bound. And then we test R15 again. If it's 0, we're done mixing. It is 0, so we didn't do any mixing on the first step, which is correct. There's nothing to mix in. Then we retrieve the base of the primes list. So RDX goes back to its original value. And it hasn't changed, so nothing actually happens. Retrieve the counter into RAX. So that becomes a 1 now. We set R12 to RCX, the pointer for our table memory. We move into R15, the byte at R12, our pointer. So R15 became a 0. So we test that, and if it's not 0, we skip. It was a 0. So that means we need to emit a prime. So first of all, we compute J. J is going to be R12 minus RCX. We put that into R14. So J is 0. Now we compute P and put it into that. That should be 3. It is. We can emit that. So we emit that into our primes list. And we increment RAX to 2. Good. We move... Here, what we're going to compute is J prime. So it's P squared. So R10 gets 3, 9, 6, 3. So that's the index of P squared. And we then add that to the table memory to make R10 into a pointer. Now we check if the pointer is inside the table memory, and it is, so we mark it, and then we start walking the table. 3 at a time. Eventually, we will end up here. R12 is our pointer into the table memory, so we increment that by 1. We check if our pointer is at the end of the table memory. It's not. So we jump up here, and now we're going to go through again. What are we emitting here? R14 is 5. 25. R10 should be 25. Ah, that's 25 in hex. We subtract R8, that's 3, so this becomes, yeah. And then we divide by 2, so this becomes, there. So all in all, it became 5, 25, 22, 11. Yep, that's what happened. And then we turn that into a pointer, check the bound, start filling in the ones, blah, 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 blah. Okay, so eventually that gets done again and again and again, and R12 gets bigger and bigger going through the whole table. And we're emitting, emitting, emitting. Eventually, we've emitted this many primes. We pop everything, and we're out. So how many primes did we get? 1,229. So let's look at that primes list real quick. By doing this primes list, count 2, 3, 5, 7, 11, 13, 17, 19, 23, not 21, not 25, not 27, 29, 31, 37. Let's see. No, 91, 97, 89. Yep. So this looks like a primes list to me. Certainly looks like it got me the primes list. Right? So that's good. It trims the memory that we use. So we said we wanted like 9,000, 10,000 of these ish. We ended up only using about 1,200 of them. So we put the rest back. Don't need this stuff anymore. We make an array to stick into the node. The node contains all that. Good. Node count, array total count becomes that. Okay, so after one round, it looks good. Now we're going to go into the more interesting part. This is the version of the prime, see if it does stuff that didn't used to happen. So we get a new max count. That max count is like big. We get the primes list. We get the sieve table. That's some like, some memory allocation going on there. But then we do this. And now when we read R15, it's not null. Yeah, it's a pointer now. So then we go, okay, is that null? And the answer is no. So we skip emitting the 2. We don't emit 2 again. We make R8 into an odd number. We move R9, which is our one pass last, 100,000 into R12, and we turn R9 into an I bound. So R9 is now this like smaller thing than R12, the one pass last. Then R13 becomes a pointer version of the I bound. We test R15, it's not 0, so now we're doing mixing. Okay, so we grab R15 plus 8. R14 is a pointer. R10 is a count, 1, 2, 2, 9, that's the right count. So R10 is another pointer that's R14 plus that count. Compare, they're fine. So R11 gets the prime at R14, so that should be 2. It is. And then we check if it's 2, and if it is, we skip it. We don't mix 2 in. And then we go back in, then we get a new one. Now it's 3, good. So now we are not going to skip it, for that reason at least. We square it into RAX, so there's 9. And then we compare that to R12, our one pass last. And if it's greater than or equal to our one pass last, then we're done mixing. But it's not. 9 is smaller than 100,000. So now we compute K. K is living in R11. No, wait, sorry. K is living in RAX. That's this thing. So that's the first time a multiple of 3 shows up that is at least as big as M prime. And so then we go, okay, it'd be curious to see what that is. R11 or RAX? What's K? 3, 3, 3, 4. Okay. So that's not 10 bigger than or equal to 10,000. But then I do this comparison here. That doesn't matter because RAX is not less than R prime 3. So we then multiply K, which is 3334 by 3 into RAX. We get this. So that is a multiple of 3, and it's the first multiple of 3 after that's at least 10,000. And then we convert that into an index in RAX. So 0 because it's the first, let's see, 1,000 and, oh, that's a bug. Okay, let's see that again. So what happened here is we were trying to compute x. X is the first number in the table we want to mark. And we got that by doing k times p. P is the prime, and k is a multiplier that makes p just large enough to get inside the range that we're trying to mark, like run the sieve on, right? And so we're multiplying them, and that should be good, right? But we get 10,002. You see, the problem is our table doesn't contain even numbers. So when we try to convert that into an index, it doesn't work because we didn't guarantee that x was odd here. We're supposed to first make sure that x is actually a number that's in our table. So what we need to do is, in addition to all this, we need to make sure that k is odd. If we do all this work and then k is even, then that's the smallest k value that works, but we need to look at the next k value up because, you know, that will be the smallest odd one that works then. So that's fine. K times p gets computed right there. If k is even, k plus equals 1. So that's just or RAX 1. Make it odd if it was even. Okay. So now RAX is 3335 instead of 3334. When we multiply it, we get 10,005. That's the first odd multiple of 3 that's at least 10,000. We convert that into an index, and that's 2. So that is better. There are two odd numbers, 10,001, 10,003, that don't get marked by mixing this prime. So then we mix this prime in, and this is just marking a bunch of 1s. So we don't necessarily need to watch this. Eventually we're going to go here. R14 is a pointer looking at prime numbers, so we increment by 4. We go to mixing 1. Mixing 1 says make sure we're still inside the list, the range of the array. And then we grab that. That should be a 5. It is. So we're going to go ahead and mix it. K is already odd, so nothing happens. Okay, so there's our first multiple of 5. We start marking that. I want to see what this looks like when we're done mixing. Okay. So RCX is our table memory. Let's look at U8 pointer RCX 100, 10,000, 100,000 minus 10,000 is 9,000, 90,000. So 10,001, 10,003, 10,005 are all marked. So let's go double check this real quick. Okay, 10,000, is it prime? It's divisible by 2. 10,001, is it prime? It's divisible by 73. 10,003, is it prime? It's divisible by 7. 10,005, is it prime? It's divisible by 3. 10,007, is it prime? It's prime. So it looks like it worked. The first 3 odd numbers weren't prime, but this one is prime. Let's look at one more. 9. Is it prime? Hey, it's prime. Okay. So now what we're expecting is when we get started, it's going to find a couple. So we test R15. R15 contains a 1. So we're looking at the first 3 steps in the table. Those should all get skipped. Then this one gives us a prime. So we say, what's the prime? R14 tells us that it's, well, let's take a look in the watch window. R14 tells us that our prime is 10,007. Good. Then we move that into the memory of our prime list and increment our counter. So our counter goes up to 1. Good. So I'm going to just run this. I guess step out of a function doesn't work in assembly code. It's kind of lame. I'm going to just run to here. So we can step in here. It looked like all that worked. So let's go to the end of that. And what's our count? So we got 8,000 more primes. Okay, cool. So now we put back what we didn't use. So we asked for 90,000, we only used 8,000. So we put back almost 80,000 or more than 80,000 U32s there, which is good. We allocate a new node, stick it onto the node list. So our total count is still not quite 101,000, which is what we're looking for, I think, right? So what was the original problem? 10,000. So we're looking for the 10,001st prime. We're not quite there. So this one is going to have a max count that's even bigger because now we're going from 100,000 to 1,000,000. We run the sieve, we get 68,000 more primes. Usually we're getting lots and lots of primes still. Let's take a look at and see if those primes look good still. So primes list, give me the first 100 in the list. Is that prime? Just sanity testing everything. What about the one before it that we would have tested? Nope. What about the one after it? Nope. Okay, so those aren't prime, but it says 1,9 is a prime. Oops, 1,9 is a prime. That's a prime, but what about this? Is that a prime? No. What about this? No, of course not. This? No. This? No. This? No. Okay, so if none of those are primes, what about the 43? Is that a prime? That's a prime. And the 49? That's a prime. The 57? That's a prime. Okay, so it looks like it's working. That's kind of crazy. It's a lot of code for it to work first time, but it looks like we got what we wanted. So now the goal is to, let's just wrap this up right here. So we kind of did plenty of assembly programming here. We spent 3 hours on just this one problem. Let's wrap it up. So we're going to grab the first 1,000 there, and then what I'm going to do is I'm going to go in a loop. I'm just going to do a loop forever. We're going to have our n start at 10,000, and then we're going to say, I'll have like low equals 3, high equals 10,000, prime C from low to high if prime's total count is greater than or equal to, see, our target is 10,001, then break. Otherwise, we do low equals high. Do we want to like double? So we should stop relatively close to the target. And then what we do is we go counter equals 0. We do a loop over our list nodes. So primes first, we go over all of these. the counter plus equals, okay, if counter plus node count is greater than or equal to 10, so we're like, here's the index we're looking for, right? We want to find index 10,001. If our counter plus our node count is greater than or equal to that amount, then our counter, let's do it this way. If it's strictly less than that, break. Answer equals 0. Then answer equals node. So node doesn't actually have a count. Node has an array count. Then node array v index minus counter gives us our answer. We break out. Otherwise, counter goes up by however many we skipped on that node. So each node we look at, we say, how many do you have? And then we skip it if it doesn't have enough to give us our index yet. And we keep track of how many we've skipped. Eventually, we'll find a node that contains enough slots, plus we'll have enough skipped that the index must be there. Then we'll find the answer, and then we'll print it out, right? All right, so let's just sanity test this real quick. So what is number 1? 0. Doesn't make a lot of sense. If I'm looking for index 0, let me see what's going wrong here. Total count looks good. So we break. Answer equals 0. Primes if counter. Oh, whoops. If index is less than the counter plus the count. Well, yeah. If index is less than the counter plus count, then index minus counter is where we want to go. Boom. So there is 0, 1, the 10th prime, the 100th prime, the 10,001st prime. Oh, okay. Oh no, that's not it. Okay. So what went wrong? We typed in the right thing, right? So it works for low values. So either our prime list is just wrong for some reason, which could be true. Or, okay, so here's what we can do. Let's test this by saying, you know what, screw it. We know our answer is probably not more than 100 million. Can we just do that real quick? That gives us the same result, and I betcha, let's just check, that we have a node count right here. Oh, I know what happened. But let's finish this off. So here, so node count of 1. Okay. So we can actually sieve pretty quickly a giant amount. I like the idea that we have a sieve extender so we can sieve just as much as we want, like sort of incrementally in batches. That was a cool thing to work out. We got to do some linked list iteration in x64 and deal with some more complicated loops. But here's what's wrong. The 10,001st is using cardinal numbers, which is 1 based. We are using C, which is 0 based, and so the 10,001st is the one at index 10,000. Here's our answer. There we go. Okay, I'm gonna take a short break, but I'll keep going tonight because we've got I've got enough energy to take a look, at least a look at the next problem, if not try to solve it. But yeah, that one took a while. All right, let's do this one real quick, because, I mean, not that I want to skip to one that's just going to literally be trivial, but the other ones are, like, I'm not in the mood for this. We'll probably do this one next time, but, like, I'm not in the mood for, like, setting up, parsing this out of a table or something, like a text file or whatever I would have to do. And I'm also not in the mood for this. This one's a cool one. I really like it, but it's too big of a thing to get started with, like, about an hour maximum left. This one, on the other hand, we can just knock it out real quick. So let's take a look. The sum of the primes below 10 is 2 plus 3 plus 5 plus 7 equals 17. Find the sum of all the primes below 2 million. So we've just been working on primes, and we know we can do 2 million. So we could just, like, just solve this using the prime see if we already have. I don't see any reason why we should do any more than that. Except maybe we'll, yeah, there's not a lot. is not a lot for us to do in assembly that we haven't already done, right? So I'm just gonna, like, all we would have to do that's kind of interesting is we could write a summer that, like, sums one of these U32 lists, I suppose, and returns the result, but, like, it's not even that interesting. Yeah, there's not really anything about that that I find, like, compelling to go and do. It would be a little bit more practice with this linked list iteration. Although, I mean, this is also overkill because I know I'm getting one node, so what I actually need is just if I run this heap once, I have one node. I grab my array, and then I go over that array. Add in all the integers, right? Just get this one done. Score some points on the, score some points and get another problem up here. Heck yeah. All right, what's next? So we skipped these two. So what's this one? Nope, not doing this kind of one. We'll maybe touch those next time. All right, highly divisible triangle numbers. Maybe this is the one we'll try to end on if it doesn't look too complicated. The sequence of triangle numbers is generated by adding the natural numbers. Yeah, so we've done triangle numbers. We know where triangle numbers come from. Let us list the factors of the first 7 triangle numbers. 1, 3. You mean the divisors? They said factors, but I think they mean factors as in the non-prime factors sense, I guess. So the divisors and factors could mean the same thing if that's what they are, how they're using it. Yes, we can see that 28 is the first triangle number to have over 5 divisors. Yes, 28 has 6 divisors. What is the value of the first triangle number to have over 500 divisors? So that's interesting because we could solve that by saying, I think it'd be interesting just to be able to answer the question, given any n, how many divisors does it have? Now maybe it's easier because it's a triangle number. There might be like an easier way to figure out how many divisors it has, but I don't know about that. But I think if we want to say how many divisors does a number have, that's kind of an interesting problem. It might be kind of a complicated one, but I think it's one I know how to solve. Let's sketch it out for a bit and see what we come up with. So this is, we're doing problem number 12. We skipped a bunch. Okay. Counting divisors. So let's just do it like this. So I'm going to say d of n is equal to the number of natural numbers that divide n. So now let's make a little table and explore this one. So 1 can be divided by 1, 2 can be divided by 1 and 2, 3 can be divided by 1 and 3, 4 can be divided by 1, 2, and 4, 5 can be divided by 1 and 5. 6 can be divided by 1, 2, 3, and 6. That's 4, 7, That's going to be 1 and 7, 8, 1, 2, 4, and 8. That's 4, 9, 1, 3, and 9. That's 3. 10, 1, 2, 5, and 10. That's 4. 11, 1 and 11. That's 2. 12, 1, 2, 3, 4, 6, and 12. That's 6. Okay. So I think this is a pretty like standard pattern here, right? So first of all, if you have a prime, like this is the only one that has 1 because everything else can be divided by 1 and something else, right? So like 2 can be divided by 1 and 2, so everything can be divided by 1 in itself. 1 is the only thing where that only gives you one answer. Primes only give you 2 answers, right? That's the definition of a prime. So primes, it's like observations. When n is greater than 1, 1 divides n, and n divides n gives at least 2 divisors. So n greater than 1 implies that d of n is greater than 1, right? When n is prime, 1 divides n, and n divides n gives all of the divisors, and therefore n prime tells us that d of n equals 2. Hey, I've seen some new folks are joining chat, so I'll just explain real quick. We're working on how to count the divisors of a natural number, and then we're going to write some code to implement that function once we've sort of worked out the details. Okay, so now the next thing I'll look at is this case, right? So 4 and 9, they're not prime, and they're not 1. But these are when n equals 1 prime number to some power, right? So 4 is 2 squared, actually 8 is also in this case. 8 is 2 cubed, 9 is 3 squared, right? So these are primed to a specific power. And then you can see that we get like 1 divides n, p divides n, dot dot dot, oh wait, let me keep going. P squared divides n, dot dot dot, p to the r divides n. And nothing else is ever going to divide n because all of the prime factors of n are p. So we've just listed them all. It's like you can raise it to one of those powers and that's it. There's not going to be any number that divides n that isn't in one of those forms. So like 3 is our answer for 4 and 9 because we get 1, 2, and 2 squared, 1, 3, and 3 squared. 4 is our answer for 8 because we get 1, 2, 2 squared, and 2 cubed, right? Those are the ways to divide 8. So we get, that gives us all of the divisors so n is equal to p to the r, tells us that the divisors of n are r plus 1, right? 1 for the 1 and 1 for each of the powers of p. And then finally, we can like understand now how it'll work when we put together like this case. So this one, and this one are composites with multiple different prime factors. So let's look at the case of 6, right? So we get 1, let's look at 6 in particular. 1, 2, 3, and 6. So here, you could look at it like the prime factorization of 6 was 2 to the 1, 3 to the 1. So, so like this one is generated by combining those. Okay, let's look at 2 examples side by side. I think that will make it a little bit more clear how this works. 12 equals 2 squared times 3 to the first. And that gives us 1, 2, 3, 4, 6, and 12. Now we can break these down further by going which prime factors, I'm going to put dotted lines here, which prime factors from here are going into the divisors, right? So here, there's no prime factors going into the divisor. Here we have the 2, here we have the 3, and here we have the 2 and the 3. Okay, here we have none, 2, 3, 2 and 2, 2 and 3, and 2, 2 and 3. All right, so what's happening is you're basically saying how many ways are there to combine these so that you get all, like unique combinations. And every unique combination gives you a divisor, and that's all of the divisors, right? You can't have a divisor that has a prime that doesn't show up in here. So we just need to be able to count all the ways to do that. And it doesn't matter. So if we had like 2 and 2, the order of those don't matter. So the fact that we took 2 2s gave us 4, and the fact that we took 2 2s and a 3 gives us 12, and so on. Which order you take them in doesn't matter. So what this comes down to is how many ways are there to take 2 out of this? There are 3, right? That's what we did right here, right? So when we were looking at things that were just a single prime, it was like you could take 0 of them, 1 of them, or 2 of them. How many ways are there to take the 3? Well, you could take 0 of them or 1 of them. So what you end up with is that for everything else, when n equals p sub 1, r sub 1, p sub 2, r sub 2, dot, 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 p sub n, r sub n, well, then we're going to get that d of n equals r sub 1 plus 1 times r sub 2 plus 1, right? We're just talking about all the ways to combine all of those, whoops, let me do the dot, 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 I skipped it, times dot, 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 r sub n plus 1, right? So you're basically looking at just the powers from the different factors, right? And the reason for that is each one of those gives you how many ways there are to put that particular prime into the mix when you're building a divisor. And then if you want to look at all the combinations, you're just saying, okay, it's like, you know, basic counting thing. I can make any combination I want out of R1 plus 1 selections from this category, R2 plus 1 selections out of this category, and so on. So we just multiply together all the different counts we get from each individual category, and that gives us the whole thing. So this is the fully generalized function. So in order to do that, we need a factor table. So that's what we're going to do next. Now I've explained before how we'll do a factor table, but I'm going to go back and refresh our memory because we didn't end up doing it when it came up the first time. So a factor table is kind of like a prime sieve where you go along and you find prime numbers and then you mark off the things that you know are multiples of the prime you found. So like here we're saying here's slot number 3, and then every third slot gets marked with a 3. Then we find the next prime is 5, and every fifth slot gets marked with a 5, except we're skipping the ones that are already marked with 3 in this drawing. But otherwise, all these get marked with 5s, right? And then same thing with 7 and so on. So we end up with this table that either tells us that we found a prime, or it tells us one of the prime divisors of a number, right? So like this right here will be our 9 slot, for instance. When we're trying to divide 9, we'll go, here we go, 9. And then that'll have a 3 in it. And so we'll say, okay, there's a multiple of 3 in this thing. We'll divide out the 3, and then we'll keep going and find out what else it has. And then we'll go, it's got another 3 in it. So then we find out it's got 2 3s, and then we're done. We found all of the factors, and we've completely factorized that thing. So we want to build a factorization table for, like, let's see, we're trying to find something with 500 divisors. So something with 500 divisors is going to have, if we go back to Milton here, 500 divisors means this product will be 500. So the powers will, like, we could have like 499, 2 to the 499, but that'll be huge. We'll find something with 500 divisors well before that. So instead of 2 to the 499, it could be like 5 different primes, and then each one of them contributes a little bit of them. Like you get 3 of these and 2 of these and 4 of those, and they all multiply together to give you over 500, right? So that's what we're going to expect. That, like, let's see, if you had like a ballpark here, 5 primes, so 2 times 3 times 5 times 7 times 11, that's the first 5 primes. If you just had that, you wouldn't get high enough. So then let's like square that. I'm gonna ballpark that if we shoot out to 1,000,000, we'll find, because I got 500,000 when I squared what I was looking at. If we shoot out to 1,000,000, we might find what we're looking for. And we don't actually need, well, okay, I would love to build a factorization table, but let me double check that thought process, because there's one thing about it that's kind of silly, which is we don't need to check every number. We need to check only the triangle numbers, and we could generate triangle numbers and then check each one of those. It would mean, so the factorization table can be built faster in a batch like that. Like we can go, let's see. We can go build the factorization table for a whole bunch of numbers at once and then use it, and that'll be great. But if we do that from scratch, then we have to build out to this giant factorization table, and then we're only going to actually use it to factorize. We're only going to use it to factorize the triangle numbers. So that's one thing we could do. Let me do one other thought process here, which is let me think about if there's any way to use the triangle number formula to find a shortcut. So the triangle number, what is, just as a note, the triangle number n is n times n plus 1 over 2. So what is the number of divisors of the triangle number of n? So this one is weird because I don't know any tricks for factorizing this guy easily, right? Like if we knew the factorization of n and n plus 1, it would be easy, but that's no easier than knowing the factorization of n, right? Like you have to be able to factorize the first n numbers to scan that anyways. One thing I will note is that these have n and n plus 1 have no factors in common. So we will get higher visibility much more quickly that way, right? We'll end up with more of these terms or factors because n and n plus 1 always have completely different, if some prime is in the factorization for this guy, then nope, you can't find the same prime in the next number because primes are bigger than 1. So like the next thing that's also a multiple of that prime is much later on in the sequence of numbers. So this will be more divisible if we just look at that. So what we could do is say, like, we're going to look at the first 100n and get their factorizations. So we would build a pretty small factorization table. And then what we would do is say like, okay, the factorization for the triangle number of n is, so the factorization of tri n, I'm gonna like make up this factorization function real quick. It's like sort of like sets with multiplicity. So it's like the factorization of the triangle number of n is equal to the factorization of n union with the factorization of n plus 1 minus 2 to the 1, right? So if we can build the factorization table for these guys, then we can very quickly grab a factorization for this, even though this will be quite a bit larger. And we won't necessarily want to build a factorization table that goes that far up. That'd be like, the size of our factorization table would be squared if we didn't use this trick. So let's try that. Let's build factorization tables. That seems best. Hey, Sandquirk, my tablet is a Wacom Cintiq of some variety. I went and just picked one that was, I don't know, relatively high quality, but not like the most expensive one either. All right, we're going to build a factorization table. So we have this fancy extendable sieve thing. I'm going to not use that same setup for our factorization table. Because it'll make things more complicated. We'll just use a single factorization table of some range here. Okay, so let me first write some C code to set up what we're going to do. Factorization table. Okay, so this is going to take in the arena and return the array of U32s. And we're going to say we want to use, I will pass in the array of primes explicitly like this. Let me think. So one thing I'm doing a little bit sloppy here is I need to pick the end of my table. I think what I want to do is just say I'm going to build a list of primes first. Yeah, I think that will make this simple, although it's not like the most optimal way that the factorization table could be built. You could build it from scratch like it's a sieve of its own, which maybe would be better. Yeah, let's try it. Let's try it. So we'll just do count. And that's like how much we want, how many things we want there. And what'll come back is an array that's like skips the evens. The first one is the factorization for 3, and it goes up to count, but only in the sense that it goes up to the odd ones, right? Okay, so we're gonna do 32 factorize table equals push an array onto the arena count. Then we're going to run the factorization table assembly stuff. We will pass that the memory and the count, and then Yeah, okay. Okay, we'll do that. Yeah, we'll do this a little differently than we did the other one. So this will have to be a U32 though, because it's controlling the size of a table of U32s based on like what numbers can appear in the U32. So it doesn't really make sense to say you can have more than the max U32 as the count. And then we just build our result like this. And there we go. We don't need to do anything else fancy, but I just want the C++ side to handle the arena part, so I don't have to call into functions outside of the assembly from the assembly. It's just too tedious. So then we can take a look at our factorization table. Arena, what did I say? I'm gonna go up to 1,000,000. But I will do it this way. Yeah, we'll just say put in 1,000,000, see what we get back. Well, for testing, let's say like we're gonna use 1,000 slots. Okay, so now let's write some assembly. Prime sieve. Okay. We could delete the old prime sieve, by the way. We replaced that at the beginning in the first few hours today, so that's good. Factorization table, proc, factorization table, endp. This is going to get RCX, gets our table memory pointer, and RDX gets our count. And then, okay, so here's where we have to, let's see, we're going to write down an assumption here. Assumptions. RCX is a pointer to 4 times RDX bytes cleared to 0. So we're going to rely on the C++ side to do all the initialization correctly and just call us when the cool, interesting computational part starts that isn't almost entirely bookkeeping. Okay. So we've got this 0 table. Now we're going to start running the sieve on it. We don't want to return anything from this, if I recall. Table. Yeah, so we're just going to keep this simple, right? We're going to say I equals 0. So I is going to be stored in the RAX register. So clear RAX to 0. We're going to do check if RAX is less than the count. So if RAX is greater than or equal to the count, go to done. Here's our done label. So we want to compare RAX, the counter, or I, to the count, which is RDX, and jump if greater than or equal to the done. Okay, so there's the header of the loop. We'll call this the loop 0 part. Here we'll jump back to loop 0. So there's the increment part, and that's going to just inc RAX as well. Okay, so now RAX contains I, which is our index, but our idea is that I of 0 is 3, so like the number, let's get n equals 3 plus 2 times I, right? So n is our number, and we're skipping 1 and we're skipping even numbers. So we start at 3 and then we go by 2. So we want, let's see, who's still free? So R8, we can say R8. Wait, we can use this load effective address thing for this. R8 gets its value as 3 plus I times 2. So there's our n. we want to test and see if there's a 0 in this slot first. So let me also read into, let's say, f. So we'll call f the variable here. F is going to equal whatever's at table memory indexed by I. So we're going to move into R9. That'll be our f. We're going to use the 4-byte version. The D word pointer, let's see, RCX is the table memory plus I is RAX, and that's got a stride of 4. Okay. So 4, 2, yeah. So that gives us R9. Which is that. Okay, so if that's a 0, then we have work to do. But if it's not a 0, we've already marked a value for this. So we don't want to fill, and we just skip this one, right? So we're going to do if f does not equal 0, go to loop 0 next. So here's our loop 0 next. That's how you advance the loop, and now we're going to test that. So test R9 against itself. So that is like a mask right there. So if it's a 0, we'll be able to say if that was 0, oh, if that was not 0, jump to loop 0 next. All right, so that'll skip the rest of the work. Otherwise, what we want to do is figure out what's our n. So that goes right here. We want to figure out so what we're going to do is we're going to say make m equal to n squared. We can use, let's see, R9 is free because that was how we were testing the factor the thing before. So R9 gets R8, and then we square it. And then we want to say, I'll skip giving that a name. So R9 equals n squared. And then we want to do j equals n squared minus 3 divided by 2, right? So that'll go the other way around. So here's how we figured out the number from the index. This is how we figure out the index from the number. So we do move into, no, we can't use one of these. We have n squared. We're going to subtract 3 from it. Subtract 3, and then shift to the right by 1, which is the same as dividing by 2. So now we have j in the R9 spot, and we want to go, okay, if j is greater than the count, then we're done. So here's loop 1, right? This is an internal loop. So if j is greater than or equal to the count, go to loop 0 next. We're done with this inner loop. So compare j is R9, to count, which is RDX. And jump, if that's greater than or equal to the loop 0 next. So skip the inner loop when R9, the j index, goes past the count. Here's how we do the increment for this loop. We take j, we add into j, which is in the R9 register, whatever is the n we got, so the R8 register. Okay, so there's the n. We add that into R9 to stride by that much, and then we jump back to the beginning of the loop. Now, inside the body of the loop, what we need to do is we want to fill the table memory at index j with the value n. So basically table memory j equals n. That's what we want to do. So move into table memory, that's at RCX, plus j, that's at R9, times a stride of 4, because these are U32s, and put in there, yeah, make that a D word putter, and then over here we want n. That's R8, R8D. Okay. I can hide this for now. So I'm curious to see what the factorization table looks like. So let's go look at that in the debugger. By the way, I didn't ever ask anyone, but how is the text on the debugger? Is it within readable size, or should I make it bigger? Because I kind of feel it feels small to my own taste a little bit. Okay. Hopefully that's a little bit easier to read than it has been. I don't know. Okay, so the factorization table. The factorization table at V has 1,000 elements. Exactly the number we asked for. And, okay, that's a little weird. 0, 0, 0. Oh. Why did it skip to 3 there? So this is not right. We shouldn't see any zeros. So one of the mistakes is I should emit before I go n squared. Yeah, so when I find f does not equal 0, I jump ahead. Okay, then I compute n. I should immediately set table memory I to n. This is different from the sieve, where when we find a 0 spot, we're done. We're never going to look at that spot again. With the factorization table, I want to take a moment and say this slot should have n in it. It's a prime. We want to mark the primes by putting the prime we just found into that slot of the factorization table. So this is just d word putter RCX plus, where's our I variable? That's an RAX times 4. So yeah, this thing we just read, now we're writing to it, and we're putting R8 into it. Does that fix it? Yep, 3, 5, 7. 3 is a factorization for 9, which goes in this slot. 11, 13. 3 is a factorization for 15. Interestingly, I would have thought 5 would show up there. 5, 1, 2, 3, 4, 5. Somehow 5 doesn't show up here. Why did the 3 overwrite the 5? Shouldn't the 5 have come later and overwritten the 3? Oh no, because it skips to 5 squared. So the first time it's like 25, and then we will always see 5s overriding 3s. But at 15, we skipped it because of the 5 squared trick. Okay. So yeah, this looks good. This is a factorization table. So that's step 1. So how do we actually use this? I didn't totally explain the idea, but now we can get one factor. So given any n, so the factorization is like, it's like this multi-set thing where there are elements and each element has a count. But let's see. The way we will use the factorization table is we're going to say, like, we want to figure out how to compute D. From the factorization table. Okay, how do you compute d from the factorization table? So what we'll do is step one, we have some variable n come in. Like we'll just say we're computing d. D has a parameter n, and we want to compute the number of divisors for n. So we're going to look up into our factorization table, the slot n. Now this is a little bit more complicated. Because like we skipped the even, so if n is even, it doesn't show up in the table at all, and if it's odd, we have to like adjust it so that we find the right index. So I'm skipping the part here, n to index. I'm skipping that part. But we can do all of, like, we can figure out f from the factorization table plus a little bit of other work. And so we find f. Then what we do is we go, okay, we know f divides n because it shows up in the factorization table. And so then we start a loop. Basically find max r such that f of r divides n. So this is just shorthand for a loop that will find a value r for us. And that's going to increment r one at a time until f to the r doesn't divide n. And the way you test if f to the r divides n is by just multiplying f into an accumulator and then trying to divide it and seeing if it divides cleanly or gives you a remainder, right? Once you find r, we have finally like some accumulator. So we'll say like an accumulator gets multiplied by r plus 1. So r is our the power up, remember up here. R is these guys right here, which are the powers of the primes. So we're finding the right value for r, and then we're multiplying it into an accumulator. And then we're going to jump back up. We're going to set n equal to n divided by f to the r. Remember, we're already doing divisions in this loop here, so we'll already know this, basically. But the idea is n gets updated to a new value, and then we jump back up here, and we keep doing that while n is greater than 1, right? Once we get to 1, we're done. And our accumulator will start at 1. So like this is a pretty sloppy idea, like description of it, but like these are kind of like the main stages. We use the factorization table to find a factor. Any factor will do. We then divide out as many of those as many repetitions of that factor as we can. We find out how many we divided out, and we multiply that into our accumulator. And then we take the new n that we get by pulling out all those factors, and we go back up here and repeat that until we're at 1, which can't be factorized anymore simply, and so then we're done. So we're going to write that, and that'll be it for the night. That one I think is interesting enough to write as assembly, but it's not really reusable. Well, there is one thing that's reusable, which is we could make a reusable like get factor function. So the way the get factor function will work is we have our fact table and our count and our x, and we want to return a factor. Actually, we might be able to get a couple reusable functions here. So let's start with that one. So get factor looks like this. Get factor, I'm going to call this get prime factor. So get prime factor, we'll have RCX is our fact table, RDX is our count. Technically this is EDX because it's a U32, but yeah. I'm being sloppy. I maybe should go add to-dos to check on that. Yeah, prime sieve also works that way. RCX, EDX. here I did mark it as R8D, and then I bet, okay, I used R8D. Okay, so I kind of did it right on those ones. R9, I did not do it right on that one. So let me just mark all those. To do R8D. This is just a reminder that we should maybe do a pass to like make sure we actually don't have any bugs where like the high bits are supposed to be ignored, but we're reading them anyways. I don't think that that's supposed to happen accidentally with 4-byte integers used in 8-byte registers. It's my understanding that that is only an issue for smaller sizes of parameters where that mistake can happen, because they set it up so you can't really very easily accidentally have 4-byte value in a 8-byte register where the high bits aren't cleared to 0. But I don't know for sure. It's worth checking. Figuring that stuff out is kind of the whole point of this. Okay, R8D. So this one here is like to do EDX. Should I be doing that? X to do. Actually, let's call that N. That's what I called it in the notes on Milton. R8D. Make sure I'm doing that correctly. Okay. So get prime factor. So how that's this line here. Now what we want to do is, first of all, if that's an even number, then the prime factor will just be 2 and we're done. So let's check if R8D is even. If R8D is even, go to return 2. Okay. Return 2 will be a label here where we move a 2 into RAX and return. So we're going to see, how do we want to test if something is even? So we're going to test R8D against 1. So this will mask them together. And if there's a 1 in the lowest bit, then it's odd. So if that's 0, go to return 2. Because if that's 0, then that means we have an even number. Hey, Limelord, thanks. I appreciate the feedback. Alrighty, so that's one case. If it's 2, then we're done. Another case is if it's 1. If it's just equal to 1, then we return 1. So these are like special cases that we have to handle because the factorization table doesn't handle 1 and it doesn't handle even numbers. So if RA to D equals 1, go to return 1. So that looks like compare RA to D to 1, jump if they're equal to return 1. Okay. Now we want to do, so we have N. Let's do N. I've been using the register name in the comment, which I find is less helpful than if I try to stick to a variable name in the comments. So now I want to do J equals N minus 3 over 2. So that's the thing that will convert, that'll convert this into an index. Shift right 1. That gives us yep, that gives us a divide by 2, and now we have an index. And so then what we do is we want to say F equals factorization table indexed by J. So again, we could just put this right into R8. We'll put this into RAX, because this is our return value, actually. So RCX plus J. RCX is the fact table. Oh, first we need to do if J is greater than or equal to count, go to return 0. So in that case, we can't help. You asked for an n that was bigger than what we can handle. Count has to be like, if count is 500, then we can handle up to, 3 plus 1,003. We can't handle 1,003 itself. We can handle everything up to that amount, right? So let's see. Do j is greater than or equal to count? How do I do that right? Compare R8D with EDX. Jump if that's greater than or equal to return 0. I don't actually know if these jumps are the right way to do this. Like, it might be that it's better to do like conditional move greater than or equal to 0, RAX 0, and then jump to return. It's not any, yeah, it's actually fewer instructions total. And it doesn't involve any conditional jumps, just conditional moves. Maybe I should be doing that. Let's try and write it that way. Just out of curiosity to see if, I don't think I've had one other excuse to use conditional moves so far, but let's give it a run here. Oh wait, I still need a conditional jump because I don't want to always jump to return. So this would end up becoming two conditionals back to back, with one of them being a conditional jump still. Maybe not valuable. Although I did just remember we can abbreviate this. Okay. Okay. Still don't know if this is the best way to do these like special case returns, but that's how I'm gonna handle it. Now, factorization table grabs f, puts it into RAX. So we're trying to grab from j. Where is j? J is in R8D. So R8. We need a times 4 because the factorization table is U32s. So we're starting by 4. Let's do move 0 extend D word putter. Does that work? No, you don't like doing that, do you? You don't like doing this either. How did I do this before? Is it like I just do this? And you don't freak out? Okay. And then I can return. So let's try that. Get prime factor. First I grab my factorization table. Now I'm going to do answer equals get prime factor. And I'm going to ask for a prime factor of 1001 and see what I get. Oh, I need to give it the factorization table to write. 13. 17, 1005, 5, 19. Okay, let's try 3 times 3 times 3 times 3. Should give me a 3. Nice. 3 times 3 times 3 times 5. Gives me a 5. Let's throw in 97. Gives you a 3. It's kind of funny because it doesn't go up to 9 squared, so it finds the 3 first. All right, yeah, so cool. So the factorization stuff works. Let's try an even number real quick. Cool. If I put in the number 1, no crashing. If I put in 1,000,000, you think 0, huh? Oh, because it's even, you can figure that out. Right. It's kind of funny. There you go. Okay. So we can get a prime factor. What's the next step? Find max R. So let's do that in assembly 2. So basically what we want here is a thing which you put in an n and an f, and it returns to you. So like, let me write this over here. I want a thing that's like max divide. And this is like a thing where you, like, the exact mapping it's going to do is a pair of naturals in to a pair of naturals out, but that doesn't really fully define it. So let me put it this way. Max divide of NF will equal R and n over f to the r, such that f to the r divides n and f to the r plus 1 does not divide n. So what I mean by this is f to the r divided by n will be a clean division. There will be no remainder. And if you were to make f a little bigger by raising it to the power of r plus 1 instead of to the power of r, then it would no longer work. So you've figured out how many times you can divide f is r. If you divide it one more time, you've gone too far. If you divide it less, then you could have divided it more. So this is the maximal amount of divisions you can do with f on n. And what you get back is r, the number of divisions you did, and n divided by f over r, which is the number left over after that. So we're going to make that in assembly next. And that's for implementing this part and also this part. Okay. So it's going to return, should we return, we could pack it into a U64 register. Or we could return it using a struct. Let's go for that. On a pair of U32s, A and B. Max divide. It's going to take in an N and an F, and then it's going to return in the A slot the repetitions, and in the B slot the stuff that's left over after all the divides. So let's go write that one. Max divide, proc, end proc, return. So here we got to remember it's a little weird. So RCX is our return pointer because we're returning a struct, right? And then RDX is our N. Technically it's going to be EDX. And RHD is going to be our F. Okay. And so at the end, we're going to have to move RCX into RAX because they want you to return the pointer that was passed to you when you're returning structs. Okay. That's assuming that I'm right about this. That's how this one worked. This could fit in a register technically if you packed it, but I don't think that they would. I don't think the ABI lets you do that. I'm pretty sure. I guess we'll find out. So now the way the algorithm will work is we're just going to start a loop. And in that loop, we're going to have a counter. So let's make R9 our counter. We'll call this R equals 0. And then what we'll do is at each step of the loop, all we do is we jump back to the beginning of the loop until we're done. It's an infinite loop, basically. And we do we want to move into, so let's see, r dx. So we're going to have to move n into a different thing, move n into r10. And the reason we have to do that is because the D register gets used especially by the divider, by the divide stuff. So we want to do compute n divided by f and n modulo f. So the way we do that is we move into the RAX register our n value, so R10. Yeah, we clear out the RDX register, and then we divide by F. That's our 8 register. Yep. Yeah, so like, again, we're kind of like counting on this to not have any bogus in it, which maybe is not a good thing to do. I have to like figure that stuff out. Because here I'm using a 64-bit register, but if I don't, then it's going to use the low 32 bits only of these two things, which I like, maybe that's fine, because that could be, yeah, that could be fine. We clear out that, yeah, maybe this is fine for now. I don't know, I hate having to like fuss with that. I'd sure like to figure out the pattern where it's like, it never screws up. Whether you're doing it as 4 bytes or 8 bytes or 2 bytes, like whatever you thought it was in the register, it just runs as 8 bytes and you don't ever think about it. That would be, to figure out that pattern, I'm sure it's possible. And just simplify everything so you don't have to spend any brain power or later on code gen power on figuring out which version of the register to use. I'll have to look into that more carefully. But anyways, so we do that, and now we've computed it. Now RAX contains this part, and RDX contains this part. And what we want to do is if RDX, so we'll say like if remainder does not equal 0, then go to done. So we're going to test the remainder, that's RDX, and we're going to jump, if that is not 0, to done. Done is right here. Otherwise, what we do is we're going to increment, so there's like R plus equals 1. So R is in R9, so we're going to inc R9. And then we're going to do, okay, so our counter R just went up. And then we want to do one other thing. We want to update n. So we're going to say n equals the quotient. That's this part. I might have spelled quotient wrong. Don't come here for spelling lessons. I've said it before. Okay. Move into R10 from the quotient. It's in the A register. And then we jump back up here and we go again. So if we got a clean divide, we will get a remainder of 0. And then we will increment our counter because we got another divide. And we will save the new quotient. And then we'll jump up here. Once this is done, we have our final result. And we just need to move it out to the RCX pointer. So the RCX pointer has been safe this whole time. At RCX plus 0, we have the count. So we want to put 4 bytes there from the count, which is that guy. And we want to put 4 bytes there, which is this, from n, which is this guy. All right, so that register there is our counter. This register here is our n. We save them into the first and second slots of our pair, and then we take the pointer to the pair, we put it into the return register, and we return. This is just the way the ABI likes to return structs, if that applies to this case. So now let's try that. Can I get mdiv max divide? How many times can you divide 2 from 1,024. Let's also throw in a 17 in there for good measure. So give me mdiv A, mdiv B. 32. And we get a crash. Okay. What did we get wrong? RCX. Okay, so maybe I got the ABI wrong here. So what did these registers look like? RCX does not look like a pointer. It looks like yep, so there we go. So RCX is actually just our N, which means our DX is probably our F, it is, and we don't have a return pointer. So what I'm curious about, if that's true, is how can I look at the disassembly? Let's go to the call stack. Let's look at this, and let's go look at the disassembly for this call right here. So that call, let's see, we're on this line. So that call is right here. We're doing a max divide. And before that, or let's actually look at after that. Okay, so it's saying we're gonna pack. So it's gonna put that into RAX. It's gonna then read that back into RAX. Oh man, debug code is so wild. It's gonna, so it reads out of RAX and puts it into the stack. Then it reads out of the stack and puts it into RAX. Then it reads out of RAX and puts it into the stack here. And then it puts a 1 in ECX. And yeah, here's where it's calling fprintf, right? So this is to call fprintf. Our parameters to fprintf are like RCX gets RDX, RDX gets some pointer rip relative address. It's strange, right? I don't know. I don't know why it is that we're getting, it's acting like it's putting A and B into one register. So I'm just curious if I were to do this like, hey, compiler, I'm not using a register, make them U64s on the return path. And then here, I just said like, okay, do this, do this. Okay, so that is what I wanted. So I don't understand entirely, but it seems like something I'm gonna need to understand. So when the return value can fit in a register, they do have the ABI say that you can pack it up like that, I guess. So that's interesting. So instead of what I'm doing here, we gotta just change a couple things. This is our N. This is our F. Move N into R10, ECX. Move F. We're going to move F into R8. So that's where we thought it would be when we wrote the code. So there we go. So that puts F there, N there. We clear out the 9. So 8, 10, and 9 are all getting used. Divide by F. Yep, so that's all the same. Here at the end, we have to pack the RAX register with these two things, right? So we're going to put into RAX. Let's see, the low bits will be R9, so the high bits will be R10. We're going to shift left RAX by 32, and then we're going to move. How do I move? Oh, I guess we're going to OR RAX with R9, right? Then return that. Is that the idea? So we put in the low bits, we shift them up by 32 bits. We put in the high bits, shift by 32 to put them in the high position, then we OR in the low bits. Do you like that better? And then I take U32s here. I don't put in those. Okay. I guess that's how it works. Let me go. I'm a little like, I was not expecting that. So the ABI fits in and meets requirements. Yeah, here we go. I didn't realize this. Struct2 fits in 64 bits and meets requirements for return by value. This exceeds 64 bits, so it becomes memory on the stack. Yes. Color passes at returns N64 result in RAX, so those are returned by value. A scalar value, user-defined types can be returned by value from global functions and static member functions. To return a user-defined type by value in RAX, it must have a length of 1, 2, 4, 8, 16, 32, or 64 bits. It must also have no user-defined constructor, so this is C++ stuff. It can have no private or protected non-static data members. And no non-static data members of reference type. It's more C++ nonsense. It can't have base classes or virtual functions, C++, and it can only have data members that also meet these requirements. This definition is essentially the same as C++03 plain old data type. Because the definition has changed in C++11 standard, we don't recommend using is_POD for this test. Otherwise, the color must, okay. For the return value, okay. So this is, I got it. So I oversimplified it a little bit. It's not any struct at all. It's any struct that exceeds the size of a register, but any struct that is like the size of an, or like if I had a 24-bit struct, if I had the thing that was 24 bytes, they wouldn't put that in a register. This is saying it's got to be like one of the sort of integer style sizes. Okay, so we have max divide. We have the factorization table. So let's wrap it up. I'm kind of like, we've done several episodes where I practiced calling functions, so I'm not so interested in like writing this very simple loop in assembly. I think we've done enough practice, so let's wrap this problem up using the tools we built by just writing a little bit of C++ code to throw away at the end. So we're gonna, oh wait, no, because never mind, I take it back. I want a reusable thing that's like count divisors. So anything I'm gonna make that's reusable, I'm gonna throw into this side. So C, we gotta do one more. C linkage, U32, count divisors. That needs the factorization table and the n. So count divisors. Here we go. All right, let me make this the divisor count function. Okay. So divisor count proc well, you can't have more divisors than the size of n. So still 32-bit, I guess. End p. Here we're going to have the fact table is in RCX. The count, or in EDX, we'll have the count. In R8D, we'll have the n. And now we're implementing this loop. So we want an accumulator. So we're going to say accum equals 1. Our accumulator will be R9. we're going to have a little test here. So loop 0. All right, if n is equal, less than or equal to 1, go to done. Here's done, return, RAX is going to get the accumulator at the end. So jump to loop 0, just a perpetual loop. Oh wait, I didn't write the if. Compare, I'm definitely fading out a little bit. I gotta wrap it up soon. So compare R8 to 1, jump if less than or equal. I gotta be careful. Let me go to check something, because there's something else that I haven't been careful about yet, which is there's like if less or equal. So LE stands for less or equal. Let me go to jump, JCC, I believe, yeah. So if I say like jump less or equal, that's this guy here. If I then go to jump if below or equal, it's like, why is that different? This is CF equals 1 or ZF equals 1. This one up here, jump less or equal, is ZF equals 1 and SF does not equal OF. They're different. So why do they sound like the same thing but they're different? And I think it's because one of them is signed and one of them is not. I'm curious if it like says anything about signed. The target instruction, a signed offset is encoded as a sign. Okay, yeah. Less and greater are used for comparisons of signed integers, and the terms above and below are used for unsigned integers. I should probably do another to-do, which is like above, below for unsigned integers. That's something I've not been doing correctly yet, but let's start doing it correctly right now. Okay, so instead of jump less or equal, we're going to say jump, because what will happen is if I'm comparing to the 32-bit integer here, and it looks like a negative, but it's actually supposed to be unsigned, then the fact that it looks like a negative because it was a very large unsigned integer, will look like a negative signed integer. They'll have the same bit pattern, right? It's the same data, but if you treat it as signed, then it's less than 1. If you treat it as unsigned, it's greater than 1. So below or equal, jump below or equal to done, right? Okay, so there's our exit condition. Now I want to, let's see, so I gotta run get prime factor. Get prime factor. Okay, so this is where it gets a little bit tedious. We're gonna have to use a couple of these registers, so we gotta save them and restore them later. Because when we do function calls, we lose the registers that are like default ones. So we're gonna set this as our accumulator. Factorization table. Where do I want to do this? I could just store this onto the stack. I'm gonna have to just read it off every time. So why don't we just grab one more of these? Here's our accumulator. Actually, I'm gonna need one for all of them. All right. Okay. Okay. Move fact table to RSI. We'll just do these one at a time. So factorization table goes into RSI. We want to just not forget these, and this seems like the easy way to do it. Move EDX, no, move count to RDI, into RDI from EDX, so into EDI. Move N to R12. And then we're going to use R13 as our accumulator. So N is now R12D. If that's below or equal, then jump to done. So what's up? We need to do call get prime factor. So that's going to be like this. But in order to do that, we need to fill these out again. So RCX gets filled in from RSI. There's our factorization table. Our EDX gets filled in from EDI. So there's parameter 2. Parameter 3 goes into R8. N, that comes from R12. So that'll give us a prime factor in RAX. So call get prime factor, and then we get a result. That's our prime factor. So we'll say we have an F. So we called this on fact table count N. F is in RAX. And then we do call divisor count. No, call max divide. Let's see, N. F, right? So we want to put N into the first parameter. So ECX comes from R12D. We want to put F into the second parameter. So EDX comes from EAX. EAX is the A register containing F. So we've set up the parameters. We call max divide. And then finally, this pair is living in RAX. So R and N prime are in RAX. So our accumulator times equals R. So we want to get, let's see, we want to move something in, we can use any register other than A. Well, EAX contains, yeah, okay. So we can actually just do IMUL, the accumulator, R13D by EAX. So that'll give us the low 32 bits of the A register, which is R, and the low 32 bits of the 13 register, which is our accumulator, multiplied together. But that's not quite right. We want to do something like, let's grab, we can use any of these volatile registers now because we are done with calls. So we'll grab this with this, and then we want to inc that by 1, and then do that, because right, this is actually times R plus 1. So we put that into the accumulator. And then we want to update n. So we want to let n equal n prime. So the thing that carries n around is R12. So R12 is going to get it, but first we want to shift left RAX by 32, because the high bits of RAX contain our new n, and then we can move into R12 from EAX, right? So that'll put n prime. First we throw away R because we're done with it, and we put n into R12, and then we loop. Okay, so can we get the divisor count of 12? We did this one earlier. We said the divisor count of 12 is 6. Let's see if our code agrees with our mental math. Oh, right, I have to pass it the factorization table as well. 2, so that's not right. Let's debug that by stepping through it and see what happened. Confusing. Okay, there we go. I'm done with this assembly for now. I'm going to trust the factorization table is correct, and I'm going to go straight into the divisor count. Okay. Each of those gets set up. So let's look at the registers. R13 contains a 1. We compare R12. R12 is R12 to 1. It's not below yet. So then we do a call to get prime factor. Boom. We get a prime factor of 2. So out pops the answer 2 as a prime factor. And we say, can we find out how many times you can divide 12 by 2? And it says one, 2, and that's it. And so ultimately we find out that there are 2 ways you can divide it twice, and you have 3 left over. So R13 gets 3. So we just found 3. We've multiplied the accumulator by 3, right? 1, 2, and 4 are the 3 cases we got from the factor 2. And then we update R12. It looks like 0 now. EAX, shift left. I shifted it left. I should have shifted it right. Shift right. Trying to get to the high bits, I need to shift right to throw away the low bits. Now I'm getting a 1. Okay, so progress in the wrong direction. So I shift right, I get a 3, and I move that into R12, our thing tracking n. We check that, it's still not low enough. So I say, give me a prime factor. I put my table in RCX, I put the count in EDX, I put 3 in R8, I call it. It says 3 is a divisor of that. I say, okay, how many times can you divide 3 by 3? Max divide comes back and says, you can divide it once and you get 1 left over. So I move EAX, a 1, into ECX. So here's a 1 in our C register. I increment it. I multiply 13 by that much. Wait, if 13 is my accumulator, why am I returning 9? That's just garbage. Please return R13, the accumulator. There we go, so we got 6. Now we can finish up. So we're gonna say, let's grab a factor table of 1,000,000 slots. It takes about 4 megabytes to do that, not a big deal. And then we're going to say, start a for loop. We'll say n equals 1 at the beginning. Forever loop, give me the triangle number of n. At each stage, we're gonna n plus equals 1. Actually, don't give me the triangle number of n. What we're gonna do is we're gonna say, so if 1,000,000, so let me take a, let me take a simplification here. Let's take about 10,000. That's a lot smaller. And then we're gonna use that trick we talked about earlier, right? So like, we're gonna have, okay, so we're gonna have n1 equals n plus 1. And then we're gonna have, well, no. We're gonna do d1 is the divisors, d0 will be the divisors of n. So divisor count n. d1 will be divisor count n plus 1. But then what we actually want to do is go like, actually, okay, I see what I need to do. So first of all, let's do m0 equals n, m1 equals n plus 1 if n modulo 2 equals 0. So if n is even, then m0 gets divided by 2. Otherwise, m1 gets divided by 2, right? So one of these has to absorb the divide by 2, and we want it to be the even one. One of them has to be even. So the even one of those two things absorbs the divide by 2. Remember, the triangle number of n equals n times n plus 1 over 2. So what we're trying to do is figure out how many divisors there are in this thing, which is going to be, it's completely, so the number of divisors in this and times this, where whichever one is even loses one of their 2's, will be the answer, right? There are no shared primes between these two things. They have completely separate sets of primes, which means when we multiply them together, the r's from one of them and the r's from another one won't add together. They will only multiply. They're completely multiplicative. Another way to put it is n and n plus 1 are coprime, and this is a multiplicative function with the property that whenever you combine two numbers, like if d of a times b is equal to d of a times d of b, right? If a and b are coprime. So the main way to think about it is just, we're trying to look at the prime factorization. The prime factorization of this and this have no overlaps. So we'll be able to use the prime factorization of one of them to calculate its d, the prime factorization of the other to calculate its d, and the combined prime factorization would have no overlaps, so it would just be the multiplication of those two separate things. But one of them has to absorb the divide by 2. That's the whole train of thought. Hopefully that makes sense. And then our divisor count, and this is cool because now I don't think we have to test very many triangle numbers before we find, like, we would have to test 1,000,000. Well, I think we would need to go up to like 1,000,000 probably to find something with 500 factors or 500 divisors. But we'll get to 1,000,000 a lot faster using triangle numbers. And so like we actually don't actually need as big of a factorization table, which is cool. So our final D is just D0 times D1. If D is greater than or equal to 500, then answer equals N, and we can break. So this is all to compute answer. And what we'll say is like N has to stay less than however big our factorization table lets us go to. Like that big, right? It has to stay like in that range. Because if we have 10,000 slots, that means we can get up to 20,000. Since we're skipping the evens. And because we have to do this n plus 1, I can't let it go to like this part, right? So that should be roughly right. Let's see what we get. So it says that has 500 divisors and is a triangle number. Just out of curiosity, I'd kind of love to know some other things. I wish, yeah, to at least find out which triangle number it is. Wait. Oh. So what did it ask for? What is the value of the first triangle number to have over 500 digits? I must have accidentally submitted an answer at some point. So I think this, or 500 divisors, I think this is our answer. Yeah, oh man, that felt like we were kind of out on a limb between the math and the programming, but that's awesome. We got it. All right, so that will wrap it up for today. I skipped a few because I was not in the mood for this one, which involved a data table, or this one, which involved even more complicated math. And I wasn't up for, we did this one, and I wasn't up for this one, which is another data table. So next time, maybe we'll dig into data tables and the Pythagorean triplets, because there's no reason we can't do them. I was just not in the mood. Let's wrap up. If anyone wants to chat more data tables, coming up next to work out the first 10 digits. Oh, this is a cool one though. So this isn't like a grid of numbers. This is like big num. So work out the first 10 digits of the sum of the following 150 digit numbers. So what you would have to do is like figure out a way to add together numbers that don't fit into 64-bit integers, and then like find out the top 10, like the high digits, right? These aren't the modulo 10. If this was just modulo 10, you'd cut all of the high digits and you'd just run on each of these rows the last 10 digits. But it wants the high 10 digits. So you have to handle the carrying and everything, and you don't know how many digits it'll be until you do it. So that could be pretty interesting. But yeah, I'll wrap up in a minute here. I just want to peek ahead. Finding the longest Collatz chain. Combinatorial problem. How many roots are there in a 20 by 20 grid? That I would really love to do that one. We'll try to get to that one next week because I already know what it's talking about, and this would be a great one. This would be a great one to compute. What is the sum of the digits of the number 2 to the 1,000? Really? With something like this, it seems like you just compute it. This would be like another big num thing, right? We would just come up with a way to handle. I guess we could use like a squaring technique. One, two, three, four, five. Then there are 3 plus 3 plus 5 plus 4 plus 4 equals 19 letters used. 300. Oh, I don't like that. 342. You have to like figure out how to decompose this into letters. I mean, it's kind of interesting, but I don't think that would be the kind of thing I want to work on. More data tables, but an interesting shape of data. Clever method, huh? Well, it doesn't seem like it'd be that hard to come up with a clever method. Here we know the sum of that. There's 2 ways to reach this. You just pick the larger one. One way to reach this. This becomes the sum of all those. This is the larger of the sum from here and here. Yeah. This is not particularly hard to optimize into a linear thing. How many Sundays fell on the first of a month during the 20th century? But you may prefer to do some research yourself. Yes. That is an interesting problem, but it's kind of a tedious one. I'd like to think about how to like approach it though. That'd be fun. N factorial. Find the sum of the digits in the number. So another big num 1. So we got some ones coming up that we might get to later about big num, but we're looking pretty far ahead. This might be about as far as we ever get this month. Anyway, I'm gonna wrap it up. Thanks everyone for coming and hanging out, watching. I'll be back next week. Bye.